Hi everyone, this video is a compilation of all of my Chapter 2 lectures from Chapter 2 in College Algebra and Trigonometry, the 4th edition by J.S. Reddy, Marcus McWaters, and Les Skrzipek. So again, this is a compilation of all 9 lectures. If you're looking for each individual lecture, I'll put a link to the playlist in the description, but I have this compilation up in case you wanted to try and digest it all in one very long form video. So again, it's very long, don't be discouraged. If you want the individual ones, they're into the description. So thanks so much for watching, and let's get right into it. Hi everyone, welcome to Chapter 2. So Chapter P, we build some of the very basic rules of algebra, and in Chapter 1, we spend a lot of time solving equations and inequalities, and we're going to finally learn to use all of these equations and inequalities and properties here in Chapter 2. So in Chapter 2, we eventually want to work our way up to functions, and then all the various properties of functions. But we're going to take a couple sections to get there, but that'll be 2.4. Until then, we have 2.1, 2, and 3, all pretty nice, just kind of establishing what graphs are. So let's start with the plane. So the coordinate plane, as you've seen it in the past, or also known as the Cartesian plane, is kind of like a second dimension number line. What we've done in Chapter 1, and even before that, is we had just a single number line for all of our answers. We had say that x equals 5 is the answer, or x is greater than -3 is the answer. All of those answers, all those solutions sat on just one single x line. However, what we now want to eventually get to is using a coordinate plane, where not only do we have an x part of the solution, we also have a y part of the solution. So in a way, the coordinate plane is kind of like a second dimension number line, but don't necessarily need to think of it that way. We're just working our way up to 2 dimensions. So we have a horizontal line on our coordinate plane and a vertical line. That horizontal line we call the x-axis. Well, that's pretty nice, right? We just talked about a real number line. We had answers that were x's. So that horizontal line is called the x-axis. The right half of the x-axis we define to be the positive x direction, and that kind of makes sense. And then the left half would be the negative x direction. Like I said, this kind of makes sense because when we read left to right. Well, if we're reading left to right, that's kind of how x values run. They run negative to positive. We like it when things go up. Likewise, we have a vertical line called the y-axis. So not only are we going to get things with x's, we're going to get things with x's and y's simultaneously. The upper half of the y-axis is the positive y direction, and when the lower half is the negative y direction. Well, horizontal is kind of intuitive in this way because we read left to right and things increase as we go left to right. However, even though the y-axis is kind of intuitive, up means positive, down means negative, it's a little backwards because we read negative to positive left to right, but negative to positive will be up to down. So in other words, up is positive, right is positive, left is negative, down is negative. These two axes meet at what we call the origin, which has the coordinate point 0, 0. And we're going to spend a little bit more time in just a moment actually graphing coordinate points. So here is the coordinate plane. You see the x-axis that runs left to right, y-axis that runs up and down, and you see these y values are positive, these y values are negative, these x values are positive, these x values are negative. Like I was saying, we use coordinate pairs or coordinate points or ordered pairs of the form a, comma, b. So this is the same notation that we use for open intervals, right? Kind of saying everything from A to B, A not included, B not included, but we're going to use the same notation to do something different now, where A comma B is some point in 2-dimensional space. A is our horizontal location, the x coordinate. B is the y coordinate, or the vertical location. So if you're trying to figure out where some A comma B goes to, you would go to the left or right coordinate for A and up and down coordinate for B. So for example, some random AB right here, A would be the horizontal distance, B would be the vertical distance. And here you see the origin at 0, 0. Okay, well, quadrants, well, if you notice here, do you see that these two lines create 4 divided areas? we have the area above the x-axis and to the right of the y-axis, left of the y-axis and above the x-axis, and so on. Each of these four things are called quadrants. So going from the top right and working our way counterclockwise, this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. And even if we don't spend a ton of time looking at that here in algebra, you will definitely look at it in pre-calculus. So quadrant 1 would be all the locations where x and y are both positive. Quadrant 2 would be every location where x is negative but y is positive. Quadrant 3, both x and y are negative. In quadrant 4, x is positive, y is negative. So let's do some graphing. Let's graph these 6 points here. Well, let's start with just one. Let's start with 3, 1. 3, 1 says we go 3 units in the positive x direction and 1 unit in the positive y direction. Or in other words, 3 is positive, go right 3, 1 is positive, go up 1. Well, negative 2, 4, if this is positive 3, then negative 2 would be 2 units in the opposite direction. So negative 2, 4 would be 1, 2 units to the left, but still 4 units up. 1, 2, 3, 4. Negative 3, negative 4 says we're going to go 3 units to the left, 1, 2, 3, and also 4 units down, 1, 2, 3, 4. Okay. 2, negative 3 says we're going to move 2 units in the positive x direction, 1, 2, but then we're going to move 3 units down, 1, 2, 3. Negative 3, 0 says we're going to go 3 units in the negative x direction, 1, 2, 3, and we're going to move 0 units up and down since we have negative 3, 0. 0, 5 says we're not going to move left or right at all, but then we're going to go up 1, 2, 3, 4, 5 points. Okay, so I'm trying to break this down into as formal terms as possible in terms of describing it for a college level algebra class. However you have graphed points in the past, whatever is easy for you to remember, by all means, keep doing it that way. Well, what if we want to take the distance between any of these 2 points? Maybe not so hard to say from this point to this point is 3 units, but how about going from this point to this point, or even this point to this point? Well, that's where we come up with distance. We can draw a line from the origin to any point on the graph. So let's say we have the point 3, 4, and we want to draw the line from 0, 0, the origin, to 3, 4. Okay, well, this line is the distance between 0, 0 and 3, 4. But how do we find the length of this line? It's not quite that obvious. It isn't just 3 plus 4. This isn't 7 units. Okay, but what we can do is we can make a triangle with this line right here. We can go bottom leg right here. We can go upper leg, or side, however you want to word it, right? We can go this leg right here and this leg right here. And now the question is, what are the values of these 2 legs? We have a formula to tell us, the distance of this leg. We have a way to relate all 3 legs. But what is the distance of this leg? What is the distance of this leg? Well, very conveniently, you see that this leg has 1, 2, 3 units. Oh, that's the x coordinate. And you see this vertical leg has 1, 2, 3, 4 units. That's the y coordinate. So the horizontal leg has length a, or the x coordinate. Vertical leg has length b, the y coordinate. And then we say that diagonal line, the actual distance, is the hypotenuse, and we define it to have length c. Now, we relate a, b, and c using what is called Pythagorean theorem. You've probably heard it in the past. It's got some very funky applications in pre-calculus, but for here in algebra, very simply, it is a squared plus b squared equals c squared. The length of the horizontal leg squared plus the length of the vertical leg squared equals the diagonal's length squared. Okay, so if we want to find the length of that line, the hypotenuse, well, if we have the point 3, 4, then A is 3 and B is 4. So all we're going to do is plug info in to a squared plus b squared equals c squared. Well, A is 3, B is 4. We know how to square numbers. 3 squared is 9. 4 squared is 16. We know how to add. 9 plus 16 is 25. And we know from here in chapter 1, we would take the square root of both sides, get plus and minus. Square root of 25 is just 5. But for the purpose of talking about distance, distance should always be positive. So the length of that line that we drew before from 0, 0 to 3, 4 is 5 units long. Now, this is great and dandy, but what if we want to find the distance between any 2 points and not just the origin? Well, if we combine the general distance formula, if we combine Pythagorean theorem with the one-dimensional distance formula, absolute value of a minus b or absolute value of b minus a, in total, we can jump to its definition. If you have 2 points, x1, y1, and x2, y2, the distance between them is this right here. Now, you already see some squares. You see a square root. You also see this x2 minus x1, kind of like b minus a. So there is both Pythagorean theorem and the distance formula we had in chapter P. So putting that all together, we get here. It takes a little too long for us to derive, but I think you guys see the elements here. So if we want to find the distance between any 2 points, we're going to just plug things into x2, x1, and y2, y1. So let's find the distance between -2, 5 and 3, -4. Well, x1, y1 is going to be our first point. So x1 would be -2 and y1 would be 5. Likewise, q would be our second point, 3, -4. So x2 is 3 and y2 is -4. And what we're going to do is just plug in all of this information for x2, x1, y2, y1. x2 is 3, x1 is -2, y2 is -4, y1 is 5. 3 minus -2 is +5. -4 minus 5 is -9. 5 squared is 25. -9 squared is 81. And square root of 25 plus 81 is square root of 106, which is roughly 10 units. So the length of the line that connects -2, 5, and 3, -4 is roughly 10 units long. Okay, but also I want to stress that our choice for x1 and x2 doesn't matter. Intuitively, you're probably going to just use first point is x1, y2, second point is x2, y2, but I just want to show you that it doesn't matter. It doesn't matter how we define one or the other. So if we instead let 3, -4 be x1, y1, x1 is 3, y1 is -4, and then x2, y2 would be -2, 5, x2 would be -2, and y2 would be 5. So let's again plug in all of those numbers. x2 is -2, x1 is 3, y2 is 5, y1 is -4. -2 minus 3 is -5. 5 minus -4 is +9. -5 squared is 25. 9 squared is 81. Oh, and look at that. We're right back to where we got. So you're most likely going to use the first point to be x1, y1, and second point to be x2, y2. But if you're ever feeling a little funky, you're more than welcome to change it up. Okay, let's find the distance between 3, 3, and 6, 6. Well, you're probably thinking 3 and 6 are 3 units apart, so the answer must be 3 units. Let's see why that's not true. Okay, first point, let's let that be 3, 3. In that case, x1 would be 3 and y1 would be 3. Let's let the second point be 6, 6. So x2 is 6 and y2 is 6. So we're going to plug in all that information to this formula right here. x2 is 6, x1 is 3, y2 is 6, y1 is 3. 6 minus 3 is 3. 3 squared is 9. 9 plus 9 is 18. But 18, square root of 18 is 3 square root of 2. So the distance between 3, 3 and 6, 6 isn't as simple as just, oh, it's 3 apart for x's and y's, so the whole answer must be 3. No, the distance between 3, 3 and 6, 6 would be roughly like 4.2 units, since square root of 2 is 1.41. So just be careful for that. Doing this with some very ugly negative numbers. Let's let -2, -1 be x1, y1. x1 is -2, y1 is -1. x2, y2 would be -7, -3. So x2 is -7, y2 is -3. All right, let's plug in everything we know. Now just be very careful. -7 minus -2 would be -7 plus 2. So this is -5. -3 minus -1 would be -3 plus 1, or -2. -5 squared is positive 25. -2 squared is positive 4. 25 plus 4 is 29. Okay, see, not a negative in sight in our final answer. Okay, well, let's go back to doing Pythagorean theorem on the same 2 points that we started with. We said the distance from 0, 0 to 3, 4. We got our answer to be 5 using Pythagorean theorem, but that means we should also get the same answer doing the general distance formula. Well, x1, y1 would be 0, 0. x1 would be 0. y1 would be 0. x2, y2 would be 3, 4. x2 would be 3. y2 would be 4. Well, plugging in everything we got, well, conveniently, subtracting 0 doesn't change anything. 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, square root of 25 is 5. Oh, how nice. Exactly the same thing. So Pythagorean theorem is very nice when we're doing it just from the origin, but in any other case, you're probably more likely to just use the distance formula. So in the past, I've actually done baseball research. There's a video of it out there somewhere, probably unlisted. But what if we want to extend this to the real world and actually do something with something that we're familiar with? So let's talk about baseball a little bit. So on a normal Major League Baseball stadium, and even on some Little League stadiums, or Little League fields, I should say, consecutive bases are 90 feet apart. So here we have, home plate is, let's say it's 0, 0. Well, it takes us 90 units to get to first base, 90 units to get to second base, 90 units to go to third base. But now what I want to know is how far apart are opposite bases? How far apart is home from second? How apart is third from first? Well, you see 0, 0, and 90, 90, and you want to be like, well, it's 90 units, or even it's 180 units. But not quite. If you were to throw a ball from home plate to second base, throwing it 90 units would be over here. Throwing it 90 units would be over here. That would not quite match to get to second base. So let's figure out how far that is. Okay, home plate is at 0, 0. Second base is at 90, 90. So just find the distance. That's all we're looking for. Well, we would have 90 minus 0 plus 90 minus 0. 90 squared plus 90 squared would be 2 90 squareds, right? X plus X is 2X. Well, this is 90 square root of 2, which is roughly 127 feet. So that throw from home plate to second base would be 127 feet, or likewise from third to first would also be 127 feet. So get out of the idea of just looking at, 0 to 90 is 90, 0 to 90 is 90. Answer must be 90. It's a little more convoluted than that. Well, let's talk about one more thing here in 2.1, and that is midpoint. So midpoint, as it sounds, is literally the point equally distanced from two others, the point in the middle of any 2 points. If we're using the same x1, y1, x2, y2, well, this would be our formula. How do we find the point in the middle of any 2 things? Well, take their average. Add the x values together, divide by 2. Add the y values together, divide by 2. So let's find the midpoint of -3, 6, and 1, 4. x1, y1, -3, 6. x1 is -3, y1 is 6. x2, y2 would be 1, 4. x2 is 1, y2 is 4. So what we're going to do is add the x values together, divide by 2. Add the y values together, and then divide by 2. So -3 plus 1 over 2, 6 plus 4 over 2. I have these out of order. I just realized that. Okay, -3 plus 1 is -2. 4 plus 6 is 10. So -2 divided by 2, -1. 10 divided by 2, 5. Okay, that's really not all that surprising at all. Very nice. Okay. 820 and 1123. Well, x1, y1. X1 would be 8. Y1 would be 20. X2, Y2. X2 would be 11. Y2 would be 23. So we're going to add the x values, add the y values, divide each of those sums by 2. Well, we just get 19 over 2 and 43 over 2. That's it. Nothing crazy. No need to find decimals. In my classes specifically, I prefer fractions, but, somewhere around, you guys might prefer decimals. Okay. Find the midpoint of -6, -17, -12, -15. Alrighty. Well, we're going to add the x values, -6 plus -12, comma, -17 plus -15, both of them divided by 2. Well, -6 plus -12 would be -6 minus 12. -17 plus -15 is like -17 minus 15. -6 minus 12, you're $6 in debt. You spend another 12, you are now $18 in debt. -17 minus 15, you're $17 in debt. You spend another 15, you are now $32 in debt. -18 divided by 2 is -9. -32 divided by 2 is -16. Okay, so not all that crazy for midpoint. I actually think it's pretty nice. A little less careful work than distance, but of course, always be careful. And kind of like for distance formula, your choice for x1, y1, and x2, y2 doesn't matter. Okay, well, what if the pitcher's mound is the midpoint between home and second base, which at an actual baseball field, it isn't quite, but let's just say it is. So how far is the pitcher's mound from home plate? Alrighty. Well, so let's say we have 0, 0, and 90, 90, and we want to find the midpoint for them. That it's between 0, 0, 90, 90. On a real baseball diamond, it's not actually halfway between 0, 0, and 90, 90, but let's pretend it is. Well, midpoint, we're going to add the x coordinates, add the y coordinates, and we're just going to get 45, 45. So then how far apart is the pitcher's mound from any other base? Okay, well, so like I said, it's not actually in the middle of the diamond, but we're just saying it is for this example. But now let's find the distance from the pitcher's mound to third base. We haven't used third base at all in this section, so let's use it here. Okay, let's check from third base, which is 0, 90. And again, now, if we're asking how far apart the pitcher's mound is from third base, this is the distance formula. Subtract the x coordinates, subtract the y coordinates. -45 squared plus 45 squared is, -45 squared would be positive 45. And then we would get 2 times 45 squared, or 45 squared of 2, which is roughly 64. I believe on an actual diamond, the pitcher's mound is 60.5 feet away from home plate. But, in our imaginary baseball example, that's how far pitcher's mound is from any base. Okay, and that's actually it for 2.1. Chapter 2 in general is very, very long. So we're going to go section by section. We're going to do a lot of different things. So it's a lot of different information, but take each section on its own. So with that said, I will see you in 2.2. Bye. Hi, everyone. Welcome back to 2.2. So we established the coordinate plane and some interesting things about any 2 points, right? We found some distances between points. We found some midpoints between points. And what we're going to do is now graph equations. Now, graphing equations itself isn't a crazy process, but there are some very interesting things that come out of graphing. So let's just look at some basics. Well, think about when we were solving equations in chapter 1. If we plugged in some answer from our solution set, if the equation held true, then we would have, we would say that thing is a solution. Well, here in chapter 2, when we're looking at things in 2 dimensions, we now not only have a single x equals or x is greater than something, what we now have is a point that we're plugging in. So no more just x equals and plugging in things for x. What we're now going to be doing is plugging in x's and y's. So we say the coordinate point AB is a solution if it satisfies an equation when plugged in. So for example, the equation y equals x squared plus 1 has a solution 2, 5. Because if we plug in 2 for x and 5 for y, well, we get 5 equals 2 squared plus 1. We know 2 squared is 4, and 4 plus 1 is 5. This equation's true, so this is a solution. However, 3, 7 wouldn't be a solution because when we plug in 3 in for x and 7 in for y, then 3 squared is 9, 9 plus 1 is 10, and 7 doesn't equal 10. So in the graph of y equals x squared plus 1, 2, 5 will be one of the points that's included, but 3, 7 will not be. So the graph of an equation in general is actually a collection of solutions. We rarely ever think about it that way. We kind of think about them as individual points that we connect, but in all actuality, the graph of an equation is actually all the solutions associated with that equation. So just some terminology here. If y is found by plugging in x, then we say y is the dependent variable and x is the independent variable. Or in other words, what we're doing in most cases, plug in x to get some y. All right, easiest way to graph is to make what we call a table of values. And in general, maybe like plugging in values from -3 to 3 might be helpful, but that isn't going to be always your only option. So we're going to begin with a set of x values and plug them in to find corresponding y values. Well, if we plug in x's and we get y's, we have a bunch of coordinate points, x, y's, or a, b's. We're going to plot those points and then connect them. So let's say we have y equals x squared minus 3. Well, this is what your table could look like. And we're going to plug in some arbitrary x's that we want to plot. Like I said, in general, -3 to 3 isn't a horrible option, but depending on what your equation is, depending on what values are allowed, what values are easy to calculate, you might want to choose some other set of values besides just -3 to 3. Again, I'm using -3 to 3. That doesn't need to be your only option. Well, if x is -3, we're going to plug in -3. -3 squared is 9. 9 minus 3 is 6. So that means one of the solutions to this equation is -3, 6. And -3, 6 will be on the graph of y equals x squared minus 3. Let's do -2. Well, we're going to plug in -2 for x. -2 squared is 4. 4 minus 3 is 1. So the point -2, 1 is on the graph of our equation. Let's do -1. -1 squared is 1. 1 minus 3 is -2. So -1, -2 is a point. And I think you guys get the idea here. But take a second, look at all the points that we have. Okay. Now, you might notice there's some funky things about the y values and the x values, but don't think about those right now. Don't worry too much. We're going to come back to that by the end of the section. Okay, so let's take all 7 of these coordinate points and plot them. That's the first thing we did in 2.1. So all of those points are right here. And what we're going to do is connect them with a nice, smooth curve. Now, how did we know it looks like that and maybe not a little bit more jagged? Well, it comes with practice, comes with understanding what x squared looks like. It's a parabola. We haven't really defined what parabolas are, but there we go. Look for the pattern of what your graph will look like. If you can't quite figure out a pattern, graph more points. The more points you have, the easier it is to figure out what your graph is going to look like. Let's do one more. Y equals absolute value of 2x minus 4. Okay, let's plug in -3 for x. 2 times -3 is -6. -6 minus 4 is -10. Absolute value of -10 is +10. So that means we have a point at -3, 10. Let's plug in -2. 2 times -2 is -4. -4 minus 4 is -8. Absolute value of -8 is +8. Please be careful. Don't use absolute values too early. Simplify the inside before you take absolute value of anything. So we have -28 as a point. -1, 2 times -1 is -2. -2 minus 4 is -6. Absolute value of -6 is +6. So we have -1, 6. All right, at 0, 2 times 0 is 0. 0 minus 4 is -4. Absolute value of -4 is 4. Okay. What happens when we plug in 1? In the last example, value started to repeat. Are they going to do that here? Is it going to be nice, perfectly symmetrical? Keyword symmetrical here. Well, when we plug in 1, 2 times 1 is positive 2. Positive 2 minus 4 is negative 2. Negative 2, absolute value of that is positive 2. Oh, yeah, you might be able to find patterns, but don't be too quick to jump the gun, so to speak, and look for them, right? See them as they come. And if you don't see them, that's okay. You'll get better at it. All right, if we plug in 2, 2 times 2 is 4. 4 minus 4 is 0. Absolute value of 0 is 0. 2, 0. And do one more. 2 times 3 is 6. 6 minus 4 is 2. Absolute value of 2 is 2. So 3, 2 is a point. So let's plot all those points. And we actually kind of get like a check mark type of thing right here. So maybe you don't see it right away. And if you're looking at this going, I'm not really sure what's going to happen after 3, that's okay. Just plug in more points. It's not going to hurt you. If you were to plug in 4, you would have had 2 times 4 is 8. 8 minus 4 is 4. Absolute value of 4 is 4. So it's okay to plug in more points than necessary. And like I said, maybe negative 3 to 3 isn't the ultimate option. Maybe you want to do negative 2 to 5 or negative 3 to 6, right? Whatever works for you to figure out what the graph looks like, by all means, do it that way. Okay, well, that brings us to something called intercepts. And you've been wondering, why do we solve equations? We haven't solved a single equation so far in this chapter, and here we go. So intercepts are points that cross the x or y axes, or they intercept the x or y axes. So the y-intercept, I just want to go back to our graph here real fast. The y-intercept would be the point that crosses the y-axis. But let me ask you something. Ignoring the graph right here, what do all of the points that would be y-intercepts have in common? This is a y-intercept, this is a y-intercept, this is a y-intercept, this is, right? What do all of these points have in common? Well, I'll tell you since we're not talking directly, but all of them have the same x value. They all have the same x value of 0. So if you want to find the y-intercept, if you want to find where it crosses this line, set x equal to 0. And likewise, x-intercepts, we'll find that in just a second. Well, if we want the x-intercepts, we would set y equal to 0. All of these points that I'm covering with my cursor right now, well, all of them share the same y value, y equals 0. Okay, so y-intercept, you set x equal to 0 and solve for y. Then you would say 0, comma, whatever that y is your y-intercept. X-intercepts, we're going to set y to 0 and solve for x. And x comma 0 are going to be the x-intercepts. Now, you might be wondering why I'm not using y-intercepts, plural, but I'm using it for x-intercepts. Essentially, it comes down to the definition of a function in 2.4. And when we get there, we're going to say that we're not allowed to have multiple y-intercepts. But for now, it's more likely than not you're just going to have a single y-intercept. Okay, so let's find the intercepts of 12x plus 14y equals 16. If I want the y-intercept, we're going to set x equal to 0. So instead of 12x plus 14y equals 16, this is going to be 12 times 0 plus 14y equals 16. Well, 12 times 0 is just 0. 14y equals 16. We're going to divide both sides by 14. And then 16 over 14 is 8 over 7. So the point 0, comma 8 over 7 is the y-intercept. X-intercept, let's set y equal to 0. So 12x plus 14 times 0 equals 16. 12x equals 16. Divide both sides by 12. 16 over 12 is 4/3, but for x-intercepts, it would be 4/3, comma 0. So there is 0, comma, what was it? 0, comma 8 over 7, 4/3, comma 0. And actually, interestingly, when it comes to lines, if you know the x and y intercepts, you can graph them. This is only true For lines, though, we haven't really described what lines are. We'll do that in 2.3. All right, let's find the intercepts of y equals x squared minus x minus 2. Let's solve for the y-intercept first. Let's set x equal to 0. Well, 0 squared minus 0, 0 squared is 0, minus 0 is 0, minus 2 is negative 2. So 0 comma negative 2 is the y-intercept. Now we're actually going to get multiple x-intercepts here, and this is where solving equations became a big deal to us, especially in 1.3. We're going to set y equal to 0, but notice this is a quadratic equation. This is something that you would use quadratic formula for, completing the square, or even easiest, factoring. Set each factor equal to 0. X minus 2 equals 0, you would get 2. X plus 1 equals 0, you would get negative 1. So negative 1, 2 are the x-intercepts, but formally written as points, negative 1, 0, comma 2, 0. So you wouldn't be able to graph this just with those 3 points. You could if you're very careful about what you're doing, but odds are don't try and do what we just did for lines in the last example. Okay, another one. Find the intercepts of x cubed minus 9x. Y-intercept, set x equal to 0. Well, this is pretty nice. 0 cubed is 9. 9 times 0 is, 0 cubed is 0. 9 times 0 is 0. 0 minus 0 is just 0. All right, cool, nice. 0, 0 is our y-intercept. X-intercepts, we're going to set y equal to 0. So let's factor out x to solve this. X squared minus 9 is x plus 3x minus 3. And then set each of these 3 factors equal to 0. X equals 0 at just 0. X minus 3 equals 0 at 3. X plus 3 equals 0 at negative 3. All right, well, we have 3 x-intercepts. That's okay, totally fine. Okay, and what you might also notice is that the y-intercept and x-intercepts are the same, or not entirely the same. There's 2 more x-intercepts than there are y-intercept, but it's okay that the x and y-intercept match, that we repeat. That's totally fine. It just means it crosses the x and y axis at the same time. Okay, find the intercepts of x squared plus 9, square root of x squared plus 9. Y-intercept, set x equal to 0. Okay, well, 0 squared is 0. 0 plus 9 is 9. Square root of 9 is 3. So 0 comma 3 is our y-intercept. Let's do the same for x-intercept. Let's set x equal to 0, or sorry, let's set y equal to 0. Well, let's square both sides. Let's subtract 9 on both sides. And, well, we could take the square root of both sides, but we would get x equals plus and minus 3i. And we've never graphed I before. Or even easier, there's just no solution here. And that's okay. You don't always need an intercept of some type. It's okay to get no x-intercepts or no y-intercept. It entirely depends on the graph. One thing I'll also note is, we spent a decent amount of time in all of 1.4 talking about I and complex numbers, but at no point did we talk about graphing complex numbers. So almost everything we do here in chapter 2 will be entirely based upon real numbers. So don't worry about I so much when it comes to graphing. Okay, intercepts of y equals square root of x minus 9. Y-intercept, set x equal to 0. 0 minus 9 is negative 9. And we can't take the square root of negative 9. So same thing here. There just is no y-intercept. That's totally fine. X-intercept, however, let's set y equal to 0. Let's square both sides. Let's add 9 to both sides. So we get 9 comma 0 is our x-intercept. So like I said, not necessarily a rhyme or reason as to when we get x-intercepts versus y-intercepts, and that's totally okay. But now let's talk about symmetry, right? The very first example we talked about when we were making a table of values, it was symmetric over the y-axis. It was perfect on both sides of the y-axis. It matched. Well, there's a specific property of that called symmetry. So they might have symmetry about certain lines or points, and we're going to talk about symmetry again once we get to 2.4, I think, or 2.5. So graphs have symmetry over certain lines or points, like the x or y axes and the origin. Well, we can algebraically determine if something is symmetric. We don't need to graph. We don't need to, try and graph something we don't really know how it looks. So to algebraically determine if something is symmetric, we're going to do one of the following things. If we are testing for symmetry over the y-axis, we are going to replace every x with negative x and simplify. Okay, now you might be wondering why symmetry over the y-axis would change x. Well, think about it this way. Here, we had a parabola before where it was symmetric over the y-axis. Now, the y values were the same on the different parts of the symmetry. The only thing that was different were the x values, right? This would have been like x is -3. This would have been like x is +3. So if we want to check for symmetry over the y-axis, we replace x with -x. You could also think about it as like solving, solving for y-intercepts. Y-intercepts, we set x to 0, symmetry over the y-axis, replace x with -x, and then simplify. For symmetry over the x-axis, well, you probably guessed it, we're going to replace every y with -y. And then for symmetry over the origin, this is kind of weird. Long story short, replace both x with -x and y with -y and simplify. Okay, so in all of these cases, you simplify, and if the simplified equation is exactly like the original, exactly the same as the original, then it is symmetric about that axis or point. If it is not identical to where you started, it is not symmetrical over that axis or point at which you are testing. So again, just to summarize, symmetry over the y-axis, replace x with -x and simplify. If they're equal, symmetric. And you see the cases for x-axis and origin. Okay, so is 1 over x squared plus 5 symmetric over the y-axis? Okay, symmetry over the y-axis, we're going to replace x with -x. Okay, so we have y equals 1 over x squared plus 5, replace x with -x, and here's what I mean by simplifying. -x squared is the same as +x squared. Okay, and now no more simplification we need to do, so now the question is this new equation exactly the same as the original? Well, you see that this starting point, this ending point are identical, so that means we are symmetric about the y-axis. Cool. Well, there's the graph of 1 over x squared plus 5. Not the prettiest thing in the world, but you see that it is symmetric over the y-axis. 4x minus x cubed, is this symmetric over the y-axis? Well, symmetry over the y-axis, we're going to replace x with -x. So wherever we see x, write -x. So instead of 4 times x, it's going to be 4 times -x. Instead of -x cubed, it's going to be -x cubed. All right, well, 4 times -x is -4x. -x cubed itself is -x cubed, but -x cubed is +x cubed. Okay, no more simplification we can do, but now is this equation that we started with identical to the equation that we ended with? The answer is no, so this is not symmetric about the y-axis. Okay, well, you probably noticed there was something in common with that last example. There's something weird about that example. Why don't we test it over the origin? For symmetry over the origin, replace both x with -x and y with -y. Alrighty, so wherever we see x, we're going to write -x just like the last one. And wherever we see y, we're going to write -y just like, or not just like, similar to what we've already been doing. Okay, well, we just simplified the right-hand side before, but we have -y, and we want to eventually get it to look like y equals to be able to compare them. So why don't we divide everything by -1? Divide everything by -1, because -y divided by -1 is now +y. Negative 4x divided by negative 1 is positive 4x. Positive x cubed divided by negative 1 is negative x cubed. And now my question is, are these identical? And sure enough, they are. So it is symmetric about the origin. Okay. Very last thing here in 2.2, we're going to talk about graphing circles. This is going to be likely the only time we talk about circles in the entire course. So buckle up. It's not that scary. So with the help of SpongeBob, we're not talking about this or this. We are talking about circles, of course. Krusty Love from 2002, legendary episode. SpongeBob helps Mr. Krabs go on a date with Mrs. Puff. Very big deal. Okay, the formal definition of a circle is, if I ask you to define it, you're kind of like, well, I don't know. It's like this, right? It's this kind of thing. The formal definition is kind of clever, if you're not really thinking in that way, but it's a set of points that are all a fixed distance away from a center. So we have some center, all the points that are, say, 5 units away from that center. So kind of a weird way of thinking about it, but it is very true and it makes a lot of sense. That fixed distance away from the center we refer to as the radius, which we denote with the letter r. And the center is denoted by the point h, comma, k. So here's a good example of why we're not always trying to reuse the same letters over and over again. A, B, a little different, but HK would be the center of the point. Now, standard form of a circle looks like this. And this is where things are a little strange. Well, this says x minus h squared plus y minus k squared equals r squared. Well, r squared, we can take that for granted. That's not so bad. But you might be wondering why we have x minus h. Well, be very careful. Okay, if our center has positive points, let's say 3, 2. Well, if h is 3, then you plug in 3 here, and you would have x minus 3. If k was 2, you would have y minus 2. So the signs of your center in the equation are going to be backwards. If the center is positive, that part of the equation is going to be negative. So be very careful about that. So let's write the equation of a circle with a center 4, 2 and a radius 7. Well, hk would be 4, 2. So h would be 4, k would be 2, and your radius is 7. Okay, that's given to us. That's not so bad. Well, let's start with this equation right here. And again, h right away is 4 and k is 2. Radius is 7. And now you might be a little uncomfortable with that, like, oh, well, our center is positive, but these are negative. Yes, that is on purpose. Please be very careful. I'm aware this is positive and these are negative. That is by design. Okay, so there's nothing to change here, but we do know that 7 squared is positive 49. Okay, so this would be the equation of a circle whose center is at positive 4, positive 2 with a radius of 7. Let's do the same thing, but for negative 6, 3. Well, hk is negative 6, 3. So h is negative 6, k is 3. The radius is 1. So again, when we go to plug these things in, just be very careful. H is negative 6, k is 3, and radius is 1. Well, here, now we see the difference between positive center values and negative center values. X minus negative 6 is positive 6. Y minus 3 doesn't change, and 1 squared is just 1. So again, there is an element of like kind of flipping signs here, sort of. So be very careful with the signs of your center in or coming from an equation. Okay, let's do one more example of writing equations. Center is negative 5, 9, and the radius is square root of 14. HK would be negative 5, negative 9. So H is negative 5 and K is negative 9. Radius is square root of 14. That's given to us. Okay, well, x minus h plus y minus k squared equals r squared. H is negative 5. K is -9, and R is square root of 14. But here we're going to get plus plus. Here we're going to get plus plus. And square root of 14 squared is just 14. So again, I can't stress enough, be careful with centers of circles. Well, what if we want to go backwards? Alrighty, well, x minus 6 squared plus y minus 7 squared equals 100. The center is always h comma k, so in this case it would be 6, 7. Don't forget, -6 is going to mean +6, -7 is going to mean +7. Now the radius, well, in the circle equation, it's x minus h squared plus y minus k squared equals r squared. So r isn't 100, r squared is 100, which means that r is 10. So, technically you take the square root of both sides, you get r equals plus and minus 10. Kind of like hypotenuse in 2.1, it doesn't make sense to talk about, negative distance. So radius is 10. X plus 7 squared plus y plus 6 squared equals 25. Well, center is going to be backwards values, right? X minus h. This is x plus 7. So our center is going to be -7 and -6. Radius, well, r squared is 25, so r is 5. Okay, again, be careful with signs. X squared plus y squared equals 1. Well, there's nothing adding or subtracting x, so center is just 0, 0. Okay, well, radius, r squared is 1, but that also just means that r is 1. So, we could also have written our circle like this: x minus 0 squared plus y minus 0 squared equals 1. And now you kind of see a little bit more as to why the center is 0, 0. Also, this is the equation of what is called the unit circle in pre-calc. So you might see this equation again in the future. X minus 10 squared plus y plus 10 squared equals 12. Well, center, alrighty, x minus h. So h is positive. X minus h is 10. Y minus k, but k is going to be negative, right? Opposite signs. So the radius, well, r squared is 12, which means that r is square root of 12. So be careful of that as well. Let's say we wanted to graph. Well, let's do exactly what we were just doing. Extract all of the information about the circle and then go to graph it. Well, our center will be -2, +3. The radius, well, r squared is 25, so r is 5. So what we're going to do is start from the center, -2, 3, and go out 5 units. The radius, 5 units in each direction. So let's plot the center, -2, 3. Let's go 5 units up, 5 units to the right, 5 units down, and 5 units to the left, and connect those points. And that's how we get a circle. Okay, let's do it one more time. X minus 5 squared plus y plus 1 squared equals 9. Well, our center is going to be +5, -1. Well, r squared is 9, so r is 3. Okay, so start at the center and now move 3 units in every direction. There's 5, -1. Go up 3, go right 3, go down 3, go left 3. And connect those points. And that's how we graph circles. Not the scariest thing on the planet, I don't think. Okay, so that's 2.2. We are slowly working our way to functions. So we've now done what the plane is, graphs of any equation, and what we're going to do in the next section are lines. Okay, so with that said, I will see you in 2.3. Bye. Hi, everyone. Welcome back for 2.3. So in 2.1, we started talking about the coordinate plane. 2.2, we talked about any graph, how we can get any graph. And now we're going to look at the very specific study of just lines. So the entire section is just about lines. So first thing we're going to talk about is slope. So linear equations, right? We looked at linear equations in early chapter 1. And linear equations result in lines for graphs. That's not really surprising, right? Linear lines, right? So the first thing we need for a linear equation is the slope. Now, the slope of a line represents the steepness of the line. You know, how fast does it grow or how fast does it decline? How slowly does it decline, and so on. So one way that a lot of people remember this is rise over run, or in other words, the change in y divided by the change in x. So to find slope, we use the letter m, and m is given as y2 minus y1 over x2 minus x1. So same way as we found midpoint, same way as we found distance, same way as we have found a lot of different things with x1, y1, x2, y2, same thing here. So we're going to subtract the y values, divide by, subtract the x values. So rise, how much does the y change? How much do we go up and down over the course of some interval, divided by how much we changed in terms of x, how much we ran, so to speak. So if your slope is positive, your line trends upward. So positive slope goes up. If m is negative, though, your line trends downward. So positive slope, positive m is kind of like something is growing, whereas negative slope is like something is decreasing. If you have m equals 0, your line is horizontal. So if that's the case, it means the line is running, but it's not rising. So for example, if it doesn't rise, if it's horizontal, right? Horizontal, the y value doesn't change. Well, 0 divided by anything is just going to be 0. So m equals 0 are horizontal lines. Vertical lines, on the other hand, similar, but they have undefined slope. Well, vertical lines, they rise, but they don't run. Well, so if it's rising but not running, y is changing and x is not. So in that case, anything divided by 0, undefined. So in the very specific case of vertical lines, they have undefined slope, whereas horizontal is 0 slope. Very different. So let's do some practice of just finding slope. So we have 1, -1, and 3, 3. Just like we've done in the past, this can be x1, y1. This can be x2, y2. So our slope is y2 minus y1 over x2 minus x1. So we're going to take the y values, subtract them, 3 minus -1 over 3 minus 1, the x values. 3 minus -1 is just 3 plus 1. Well, 3 plus 1 is 4. 3 minus 1 is 2. So our slope is 2. So for every 1 unit that we run, we go up 2 units. Or for every 2 units that we run, we rise 4 units, and so on. Okay, let's do another one. -7.5 and 6, -3. Well, we know what the slope equation is, so we don't need to, keep remembering it each time. But here we go. Here's the slope equation. Same thing. Let's subtract the y's. -3 minus 5 over 6 minus -7. 6 minus -7 is addition, so 6 minus -7 is plus. $3 in debt, spend $5 more, you're $8 in debt. So 6 plus 7 is 13, or just -8/13. So both of these would be correct. Okay. -2, -3, and 5, 4, same thing. y2 minus y1 over x2 minus x1. Both cases, minus is plus. Well, 1. That means for every unit that we rise, we also run 1 unit. It goes up 1, right 1, up 1, right 1, up 1, right 1, and so on. But just like a lot of the other things we've talked about so far in this chapter, order doesn't matter. So using the exact same points, if we instead want to use, 1, -1 as x2, y2 for some reason, right? Maybe you just prefer going that way. And then this was x1, y1. Well, guess what? -1 minus 3, -4, 1 minus 3, -2. -4 divided by -2 is +2. Exact same answer we got in the last slide. Okay, same thing. -7.5 and 6, -3. Let's call this x2, y2, and this one x1, y1. All right. Well, okay. So 5 minus -3 is plus. $7 in debt, spend $6 more, -13. 8 over -13 is the same as -8/13. Just like the last one, right? Numerator's negative or denominator's negative. We can just write that negative on the outside. Last but not least, let's do the same thing with these last 2 points and see that we get the exact same thing. you're $3 in debt, you spend $4 more, you are $7 in debt. Or if you have $2 in debt and you spend 5, you're still $7 in debt. -7 divided by -7, anything divided by itself is 1. Okay. So that's slope. And what we want to do is write equations of lines. And we have 2 ways we do that. We have 2 ways. One is called point slope form, and the other is called slope intercept form. I personally really like slope intercept form, but a lot of people across the world don't mind slope intercept. So I'm going to be very centric to slope intercept, but don't think that point slope is necessarily bad. It's really just a preference in the way I teach. So here's the slope equation. And what if we multiply both sides by x2 minus x1? Just multiply both sides by the denominator. Well, here, this obviously cancels out. That's the whole point. And if we just rearrange terms and relabel some things, this is what is called point slope form. It's called point slope form because you have the slope m, and you would plug in any point on the line, x1 and y1. So for that reason, since you are plugging in a point and a slope, it's called point slope form. So we need 2 points to find the slope, but we only need to include one of those 2 points when we're doing point slope form. Now, it doesn't matter which one we're given. So, we need 2 points to find the slope. That we can't negotiate on. But of those 2 points, when we go to plug it into point slope form, we have a choice of using either point. So let's do just that. Let's say we have these 2 points, -3, 1 and 2, 11. I want to find point slope form, and then I want to solve for y. Okay, well, we start with the slope always. Let's subtract the y values divided by subtract the x values. 10 over 5, that's 2. Okay, well, point slope form is this equation right here. And what we're going to do is plug in 1 point and plug in the slope. So for this one, let's plug in -3, 1 for x1 and y1, and we're going to plug in 2 for m. So we get y minus y1, which is just 1, equals 2x minus -3. Okay, well, we can do one step of simplification. X minus -3 is x plus 3. And this is formally point slope form. So a lot of people in math don't mind this notation right here to write lines. But for me, let's say we want to solve for y. Okay, well, we can distribute 2, and then we can add 1 to both sides, and we get y equals 2x plus 7. Okay, I think it's a little cleaner this way. We have a name for that thing. Well, I already said it before, but we'll give it just another second until we get there. But I just also want to take the time to show you that it doesn't matter which point we use. I told you you can use either point and you should get the exact same answer. So let's do the exact same thing, but with 211 instead. So slope is still 2, right? It's the same 2 points, but we're going to plug in 2 for x1 and 11 for y1 this time. All right, we still distribute 2. This time we're going to add 11 to both sides to solve for y. You're $4 in debt, and somebody sends you $11. You now have $7 again. So point slope form, they are really the exact same line when you solve for y. Now, this solved version for point slope, right? Point slope is this version right here, or the one that we had on the previous slide. But this solved for version, this kind of cleaner version, is called slope intercept form. Because what we have is the slope m, okay, surprise, surprise. And what so happens to be the case is that b is the y-intercept. Think about that. Y-intercept is when we set x equal to 0. So if x is 0, well, m times 0 is just 0, and then 0 plus b is just b. So m is your slope, b is your y-intercept, hence slope-intercept form. Okay, so let's do some practice of finding slope-intercept form. So let's do 5, 0, and 0, 8. Let's find the line between them. I have an asterisk here just because when we get to that step, I'm going to plug in 5, 0. On the next slide, I'll show you plugging in 0, 8 and how it's the exact same thing. All right, find slope first. Subtract the y values, subtract the x values. Also, more so now than every other thing that we've kind of looked at, it's okay to change the order in which one is X1 and Y1 and X2, Y2, but just be very careful that when you do that, you stay consistent. So for example, if you're calling this X2, Y2, make sure that you do this Y minus this Y over this X minus this X. Don't magically flop and say like this is X1, Y2 and plug it in that way. That's not going to be good. So just be careful of that. Okay, so we have our slope. Here's slope-intercept form. And what we're going to do, similar to point slope form, just with a different equation, we're going to plug in slope m, but instead of plugging some point into x1, y1, we're just going to plug that point into x and y. Writing equations, you've already seen that every equation has a y and has an x, but b would be new, so we need to solve for b. Okay, so y is going to be 0, m is going to be -8/5, and x is going to be 5. We'll start by plugging in the slope, and now I'll plug in that term. All right, 5 cancels out. We're going to add 8 to both sides, and we get b equals 8. Now, that's not the end of the question. We want to write the formal equation. The formal equation says y equals -8/5 x plus 8. And that is very formally slope-intercept form. And now you see that because we have the slope -8/5 and we have the y-intercept 8. Oh, it actually happens to be right there. But just for the purpose of showing you, that's how we would get it. Well, let's do the exact same thing, but this time we're going to use 0, 8, just to show you that it doesn't matter what point we plug in. So now let's plug in 0 for x and 8 for y. All right, well, -8/5 times 0 is just 0. Oh, look at that. B is 8. So if you do this correctly, it doesn't matter what point you plug in, you should get the exact same answer for point slope, for slope-intercept form. Okay, let's do another example of that. 1120 and 814. Let's start by finding the slope. At this point, we're pros of doing this. Let's subtract the y values divided by subtract the x values. Subtract, and -6 divided by -3 is +2. Okay, so in y equals mx plus b, m is 2, and now we want to solve for b. I believe I'm going to plug in 1120 for x and y. Yeah, there we go. 2 times 11 is 22. Subtract 22 on both sides, we get that b is -2. So the answer to slope-intercept form is y equals 2x minus 2, or plus -2, but also, plus -2. It's a lot easier to just write -2. And again, for practice, try doing the same thing with 814. In this step right here, you'll see you get the exact same answer. Alrighty, let's do another set. -5, 1, and 2, 7. Subtract the y values over subtract the x values. 2 minus -5 is 2 plus 5, so we get 6/5. 6/7, sorry. Okay, well, y equals mx plus b, m is 6/7, and we're going to plug in an x and a y. I don't remember which one I use. We're going to use the second point here. Alrighty, so plug in 2 for x, 7 for y. 6/7 times 2 is 12/7. We're going to subtract 12/7 on both sides. I'm going to trust you can subtract fractions. So slope-intercept form is y equals 6/7 x plus b. B is 37/7. Okay, so now that we have slope-intercept form, we actually can now graph lines in a slightly easier way. So the easiest way to graph is to find the x and y intercepts of whatever your line is and connect them infinitely. That's the easiest way to graph lines. So let's graph y equals 4x plus 12. All right, well, let's find the y-intercept. To find the y-intercept, we set x equal to 0. So y equals 4 times 0 plus 12. Y is just 12, right? 4 times 0 is 0. 0 plus 12 is 12. So the y-intercept is 0, 12. X-intercepts, we're going to set y equal to 0. Well, 0 equals 4x plus 12. Let's subtract 12 on both sides. Let's divide both sides by 4. So the x-intercept is -3, 0. Okay, We're going to graph these 2 points, draw a line between them, and connect them infinitely. Easiest way to graph. So there's a little theory in there as to the fact that linear equations are degree 1, and and that we needed 2 points to graph it. That we'll come back to in chapter 3. But for now, it's good practice. Alrighty, 12x plus 6y equals 12. Well, first things first, let's get this into slope-intercept form. In general, it's a lot easier to deal with slope-intercept form, and it's a lot cleaner looking. This is technically called standard form, but, to each their own. Okay, so to solve for y, right, slope-intercept form has y all by itself. Let's divide everything by 6. Just kidding. Okay, let's start by dividing everything by 6. So 12x divided by 6 is 2x. 6y divided by 6 is y. 12 divided by 6 is 2. And then let's just subtract 2x on both sides. Alrighty, well, y-intercept, we're going to set x equal to 0. Well, pretty clear to see that y is just 2. Negative 2 times 0 is 0, so 0 plus 2 is 2. Y-intercept is 0, 2. X-intercept, we're going to set y equal to 0. So we're going to subtract 2 on both sides. We'll divide both sides by 2, negative 2, excuse me. So our x-intercept is just 1, 0. So we're going to graph those 2 points and connect them infinitely. Not bad. But we actually didn't need to do that. It was nice to get it into slope-intercept form, but nothing about this said we needed to put it in slope-intercept form. All we care is graphing the thing. Well, if we only just want to graph it and we don't care about what the actual line is, why don't we just go for finding the intercepts right away? Y-intercept, set x equal to 0. So 12 times 0 is 0. Divide by 6. Oh, we get 0, 2 again. And same thing for x-intercept, set y to 0. 6 times 0 is 0. Divide both sides by 12. We get x equals 1 again. So, kind of keep an eye out for what the question's asking. If somebody's not asking to get the equation of a line, maybe you don't need to. So just something to keep in mind. All right, one more example of this. 3x minus 4y equals 12. Y-intercept, let's set x equal to 0. So 3 times 0 minus 4y is 12. Well, 3 times 0 is 0. Negative 4y equals 12. Divide both sides by negative 4. So our y-intercept is 0, negative 3. X-intercept, let's set y equal to 0. All right, well, 4 times 0 is 0. Divide both sides by 3. We get 4, 0. And there we go. Okay. So that's slope-intercept form. That's how we formally graph lines. I think it's a nice, easy way of thinking about it. But let's just look at some other weird lines, because why not? Alrighty, horizontal lines. They all have a constant y value. So their form, how you would write a horizontal line, is just y equals k. If you want to think about this in terms of slope-intercept form, think about the fact that slope-intercept form, y equals mx plus b, but we said in the very beginning that horizontal lines have 0 slope. So it would be y equals 0x plus b. But 0x would just be 0. So you would just get y equals b. In that case, instead of using b, we just use k. Vertical lines have a constant x value. So similarly, this would be x equals h, where h and k in both cases are just real numbers. So for example, we have y equals 2 and x equals 4. Very, very, very exciting. So, but more interestingly, parallel and perpendicular lines. So parallel lines run side by side each other. Imagine you and your friend are running in the park and you are both running side by side each other. You are parallel to each other. So they never meet and they have the same slope, right? Maybe you and your friend aren't necessarily running at the same pace, but you are in the same direction. Just the goal is to make sure you guys never meet or crash into each other. So parallel lines don't meet, but they have the same slope. So for a line with slope m, a line parallel to it, this m parallel notation right here, well, the parallel slope to any line would be just m. Okay, now you're kind of wondering what does that mean? M parallel equals m. It just means that the parallel slope is the same as the original. Now, a line perpendicular to another line creates a right angle when it meets. So for example, if you're running in this direction, a perpendicular line runs in this direction. You kind of create like an X or a cross, and you would create a right angle where they meet. So it's a little harder to see. It'll make a lot more sense when you see it graphed. But in that case, M perpendicular, that slope is -1 over M. A good way of remembering that is flip the slope, make it negative. Not that that's easier to remember, but I think it's a little bit easier to remember this right here. Perpendicular slope, flip it, make it negative. Okay, so let's find the equations of a line parallel and perpendicular to y equals 2/3 x plus 2, each of which will pass through 2, 8. Okay, well, here we have y equals mx plus b. The parallel line slope, okay, well here, slope is 2/3. Now, the line parallel to a slope with 2/3 is also 2/3. So m is 2/3 in our question. Any parallel line will also have 2/3 slope. Perpendicular slope is going to be -1 over m, or in other words, take your slope, flip it, and make it negative. So instead of 2/3, flip it to 3/2 and make it negative. Well, now this question is just like any other question that we've dealt with in the past. Here we have a slope, we have a point. All we're going to do, y equals mx plus b. We have m is 2/3, x and y come from 2 and 8. All right, 2/3 times 2 is 4/3. Subtract 4/3 on both sides. We get, fraction, subtraction. So b is 20/3. So y equals mx plus b. M is 2/3. B is 20/3. So the line that is parallel to y equals 2/3 x plus 2 that passes through 2, 8 is this line right here. Okay, and there you go. They literally run parallel to each other, and they will never meet. That's the whole point of being parallel. Okay, well, likewise, doing this with perpendicular lines, this is the slope we want to work with. So plug in m, x, and y. Well, a little bit nicer here. 2 divided by 2 is just 1. Add 3 to both sides, we get 11. So y equals m, x plus b. And there we go. This is what a perpendicular line would look like. They cross, they make a right angle right here. A little bit easier to visualize. Okay, let's do another example of this, but let's find the equations of any parallel line and any perpendicular line when the original line is 5x plus 1. Okay, well, m is 5 here, right? Y equals mx plus b. So that means the parallel slope is just itself, and the perpendicular slope would be -1 over that slope, -1/5. Alrighty, so we have our parallel slope. We don't have a point this time. I'm just saying do any point. Well, the original equation's y-intercept is 0, 1. Well, why don't we just use 0, -4? I don't know, totally arbitrary. Well, y equals mx plus b. Plug in m, x, and y. So b is just -4. Y equals 5x minus 4. That's it. You have the slope. We found some other random y-intercept. And there we go. Not so bad. Alrighty, one more example of this. Perpendicular slope is -1/5. Original y-intercept is 0, 1. Let's use 0, -1. Why not? Let's be weird. Alrighty, y equals mx plus b. M, -1/5. X is 0. Y is -1. Oh, actually, that wasn't a bad choice because that's just going to go away. So y equals mx plus b. Y equals -1/5. X minus 1. There we go. Very, very exciting. And that's the end of 2.3. So 2.1, 2, and 3 kind of set up this very nice, like what graphs are type of deal. But what we're going to do for the entire rest of the section is, rest of the chapter is introduce functions. So functions are kind of like the study of algebra, right? We need functions to describe a lot of the things that we're going to be doing. And that's going to carry us all through the rest of the chapter and all through chapter 3. So I will see you in 2.4. Bye. Hi, everyone. Welcome back to 2.4, where we really start talking about like the big study to college algebra, and that's functions. So like I said, at the end of 2.3, functions are going to carry us through most of the rest of the way. So yeah, we're gonna get right into that here. So functions in general are rules that assign elements from one set to exactly elements in another set. So technically you can have a mapping where any number of x's go to any numbers of y, and you can have whatever you want. But for functions, we very specifically want rules or mappings where elements in some starting set x get mapped to exactly one element in some ending set y. Well, this starting set x we would refer to as the domain, and y, this ending set, we would refer to as the range. Domain is where we start, range is where we end. And maybe you're already starting to think about x's and y's. What do we usually plug in? Do we normally start with x's and find y, or do we normally start with y's and find x's? It's almost like I use the right letters when I'm defining these sets. So the rules for functions, again, is that every element in set x, every element in the beginning set x, has to be assigned to something in y. However, not everything in y has to be used. Everything in x has to be used, not everything in y. Likewise, every element in x can only go to one element in y. However, multiple x's can go to one y. It's just that x can only be used once. Y's can be used more than once, but x's may only be used once. So correspondence diagrams, we're not going to spend a whole lot of time with this, but I'm going to move to the whiteboard just to show you some examples of what would be a function and what would not be a function. Okay, so now we're on the whiteboard. Just in general, what a correspondence diagram would be is something like this, x and y. Let's say we have 1, 2, 3, 4, 5, 6, and just any mapping, just to show you what a general mapping could look like. 1 could go to 4, and 2 can go, and 2 can go to 5, and 1 can go to 5, and 3 can go to 4, and 3 can go to 6, and why not? 3 can also go to 5. Just this mapping of x's to y's. Now, I'm not going to comment on this one. This is not a function by any stretch of the imagination, but let's go into some of the properties specifically of functions. I just wanted to show you a very quick correspondence diagram. So let's say we have some set x, some set y, and we're mapping from x to y. Okay, so let's again go 1, 2, 3, 4, 5, 6, 7, 8. So the rules of functions are as follows. First rule is that every x must be used, and 2, every x can only be used once. Okay, so for example, 1 can go to 8, 2 can go to 6, 3 can go to 5, and 4 can go to 7. This checks both rules. Every x was assigned to something in y, and every x was assigned only once. So that's okay. There's nothing wrong with that. Now, another example of something that would be okay would be something like 1 goes to 5, and 2 goes to 5, and 3 goes to 5, and 4 goes to 5. Just to review the rules again, well, every x was used, and every x was used once. We don't have any rules that run against multiple y's, or y's being used multiple times. So as long as it checks these two rules, we are totally okay. All right, let's do an example of something that would not work. So for example, let's say 2 goes to 6, 3 goes to 8, and 4 goes to 7. Okay, let's go through our two rules. Every x must be used. Well, 1 wasn't used. Well, that's kind of a problem. That fails the first rule. So this, as written, is not a function because x equals 1 was never used. Okay, so that would be an example of something that isn't a function. Well, let's do another example of something that is not a function, but maybe it violates the other rule. Okay, so let's say 1 goes to 5, and 2 goes to 6, and 3 goes to 7, but 3 also wants to go to 5, and 4 goes to 8. Well, let's look. Was every x used? Yeah, 1, 2, 3, 4, 5. 1, 2, 3, 4 were all used. However, not every x was only used once. Look at 3. 3 went to 2 things. It went to 5 and it went to 7. That violates the second rule because every x was used, sorry, at least one x was used more than once. So even if one x does this bad thing, that's all that matters to make it fail. So that's how we like visually define functions. Of course, we're going to do this more with algebraic methods and terms, but I still wanted to show you this nonetheless. So I'll see you back at the presentation. And now we're back at that presentation. Okay, so let's now introduce function notation. And what we use is this f of x in parentheses. This is not f times x, right? In the past, we have used parentheses to denote multiplication. This is not that. This is f of x. Or in another way, saying the value of f, the value of your function at some x value. Okay, well, we also use y to denote the exact same thing, right? We can say that y is the value at x. So in a lot of ways, y and f of x are interchangeable. And maybe at some point in this section, we will do something where we literally interchange f of x and y. So like I said, f of x is saying value of the function at x. Y is also saying the value of your equation at x. So they're very, very similar. If you can write something as f of x equals or y equals something specific, where you get only one y value for every x, right? Correspondence diagrams. If we had something where every x only goes to one y, we are good to go, okay? They would then be a function. So let's do that algebraically. What we want to do is get exactly like I have written here, y equals one specific thing. So if we can write this as y equals where every x only goes to one y, we are good to go. Okay, so we're going to solve for y, right? That's what y equals would be. So let's subtract 6x squared on both sides, and let's divide everything by -3. Now, this, let's see, does every x go to 1y? When I plug in x, how many y's do I get back? Well, if I plug in x equals 0, totally arbitrary, let's plug in x equals 0. Well, 0 squared is 0. 2 times 0 is 0. 0 minus 4 is -4. But that doesn't really mean anything. What we're most concerned about is that when we plugged in 1x, we only got 1y back. That's the key here. So every x only goes to 1y. No matter what we plug in for x, we can only get 1y back. So this is a function. Now you're probably wondering, how could this possibly fail? Well, let's do one like this. Let's solve for y. Let's add x to the fourth to both sides. Let's take the square root of both sides. But don't forget that when you take the square root of both sides, you get plus and minus. Okay, maybe we already start to see the problem. All right, let's plug in anything for x and see how many y's we get back. Let's again plug in x equals 0, because why not? Well, 0 to the fourth is just 0. 0 plus 4 is 4. Square root of 4 is 2, but then we tack on plus and minus to that 2. So when we plugged in one single x equals 0, we got two answers back. We got +2 and we got -2. One x went to two y's. So this is not a function. Okay. X plus y cubed equals 12. Let's subtract x on both sides, and let's take the cube root this time of both sides. But think back to 1.5. In 1.5, when we take a cube root or an odd root of both sides, we do not get plus and minus. So we can take the cube root, it's not an even root, and we are good to go. Well, you already see we don't have plus and minus this time. So let's plug in x equals 0. Why not? Well, -0 is 0. 0 plus 12 is 12. Cube root of 12, no idea what it is, but point is we only got one answer back. So 1x goes to 1y. This is a function. All right, just moving up the ladder, let's say y to the fourth. You probably already know what's going to happen, but let's subtract x to the eighth, 15x to the eighth on both sides. Let's divide everything by -1. And now let's take the fourth root of both sides. But don't forget, when you take the fourth root of both sides, you again get plus and minus. Okay? And now you see, no matter what we plug in, we're going to get two y values back because of the plus and minus. So, not a function. All right. Another thing we're very interested in when it comes to things that are actually functions, not guessing and checking whether or not something is a function. Okay, we're given something, we know it's a function, we want to evaluate at specific x values. Well, to evaluate a function, simply plug in whatever value you want for x. So let's say f of x equals x squared minus 6x plus 8. Well, we moved from y equals x squared minus 6x plus 8 to just f of x equals x squared minus 6x plus 8. Let's say I want f of 3. F of x equals 3. Well, here, f of x, f of 3, the only thing that changes is wherever we see x, we're going to write 3. So plug in 3 in parentheses, and now it is just simplifying. 3 squared is 9. 6 times 3 is 18. 9 minus 18 is -9. -9 plus 8 is -1. The value at 3 is -1. That's basically the point. 3 comma -1. No different from how we have done it in the past. F of -2 says wherever we see x, plug in -2. Again, use parentheses. Be very careful. We've talked about this problem so many times. -2 squared is +4. -6 times -2 is +12. So we get 24. Okay. F of 1/2. Yeah, I know how much you guys love working with fractions, but same thing. All it says is wherever we see x, plug in 1/2. 1/2 squared is 1/4. 6 times 1/2 is 3. And I'm going to trust that you guys can add and subtract fractions. Okay, so you see the pattern here. Wherever we see x, just plug in that value. That's it. Nothing else. What if we want f of potato? Nothing says we can't do that. Well, f of potato says potato squared minus 6 times potato plus 8. Whatever we want to plug in for x, all it says is replace x with that value. Of course, potato is a little silly. I totally get it. But the idea here is it does not matter what is in here. All it says is to plug in that thing for x. So kind of moving in that same direction, what if we don't want to plug in just a single value? We want to plug in another expression. And we're going to do that quite a bit here and in the future. So f of a plus 2 just says wherever we see x, write a plus 2. So a plus 2 squared minus 6 times a plus 2 plus 8. That's it. This is foiling. This is distribution. And now just combine like terms. It doesn't always have to be something we can combine. It's okay. Alrighty, 4a minus 6a is -2a. 4 minus 12 is -8. -8 plus 8 is 0. A squared minus 2a. It's not as comfortable. I get it. We want to plug in numbers and we get numbers back. But that doesn't always have to be the case. And you're going to see in the future how we would get something useful doing something like this. Okay, for example, we can also do f of x plus h. Now, let's be very, very, very clear about something. I understand there is an x here and there is an x here. These x's are not the same thing. This is saying some single x value in space. This is saying the expression x plus h. So same thing. I know it already has an x there, and we have an x in our original function. That doesn't matter. Wherever we see x, we're going to write x plus h. And again, this is going to be foiling. You are going to FOIL, you're going to distribute, and you get to something that can't even be combined, but that is totally fine. There's actually very good use for something like this. I don't remember what section it's in. It might be in 2.5, but I can tell you for sure, those of you that have to take calculus in the future, you will see f of x plus h again. So again, wherever you see x, just plug in that thing in parentheses. All right, let's do negative 2x squared plus 5x. F of 0, wherever we see x, plug in 0. 0 squared is 0. Negative 2 times 0 is 0. 5 times 0 is 0. All right, whole thing 0. That's very exciting. F of negative 1, wherever we see x, plug in negative 1. Negative 1 squared is positive 1. Negative 2 times positive 1 is just negative 2. 5 times negative 1 is negative 5. Negative 2 minus 5, negative 7. F of x plus h, wherever we see x, we're going to write x plus h. I get it. I know it is uncomfortable because there's already an x there and you just want to plop on a plus h. Can't do that. Imagine this was an a. If this was a plus h, well, you'd already be good. You'd have nothing to worry about. But it is an a plus h. It's x plus h, and it functions exactly the same way as if it was a plus h. All right, this is foiling. This is distribution. All righty, FOIL the insides, then distribute negative 2, and that's all you get. We have to leave it like that for right now, and that's okay. Okay, well, that's the basics of function. That's probably one of our longest basics we've had in a long time, but yeah, so it goes. All right, domain and range. Well, domain and range, we talked about on that very beginning slide. Domain is the set of all places we start, and range is all the places that we end. So domain, in general, for algebraic functions, not like what we were doing before, is the set of all real numbers for which our algebraic function is defined. And we always write these things as intervals. Okay, another good way of thinking about it is the set of all x values that are included. Okay, what I mean by that is take the set of x values that when you plug it in, you get something normal back. You don't get like 2 over 0 or square root of negative 3. So by default, a function's domain is negative infinity to infinity, or all real numbers. However, we have some red flags that we need to bring up when they happen. First one is for rational functions. Rational functions are just functions with a denominator. And in that case, well, think about what causes problems when we're in a denominator. We can't divide by 0. So in rational functions, the denominator cannot be equal to 0. Okay. Square root functions. Well, we know we can't take a square root of a negative number, so we need to make sure the inside is not negative. If you have a square root in the denominator, well, kind of like a combination of the previous two examples. These two are kind of red flags on their own, these first two bullets. This third bullet, though, is a nice combination of them. Well, we just said square roots. The inside of a square root can't be negative. So that means it can be 0 and it can be positive, but if it's in the denominator, it also can't be equal to 0. So long story short, inside must be positive. Not just negative, must be positive. So it can't be 0, it can't be negative, it has to be positive. If you have a rational and a square root, so for example, you have a square root in the numerator and there's still a denominator that causes problems, find the domains of each part and then take their intersection. This happens not frequently enough for us to, spend a whole lot of time doing it. So let's find some domains. Find the domain of 400x squared plus 236x plus 19,003. Well, look at the red flags that we have. We have rational functions, we have square root functions, and all even root functions, right? We can't take negatives inside an even root. But rationals, fractions, square roots, those are our red flags, and we don't have either of those here. How nice. There is no rational, there's no denominator, and there's no square root, so we have nothing to worry about. No denominator, no square root. By default, our domain is all real numbers, negative infinity to infinity. What this says is that you can plug in anything you want for x, and you will always get a defined number back. It might not always be a pretty number. It might be very big, or in this case, can anything be negative? I don't even think so. So, it might be very, very big and very, very ugly, but the point is it's defined. And that's the key to domain. Find the domain of 1 over 2x minus 6. Well, this is a rational function. It has a fraction. It has a denominator. And we want to make sure that the denominator never equals 0, right? The only place that this could be undefined is when the denominator is 0. Well, rational denominator cannot equal 0, so we set the denominator not equal to 0. You can similarly set it equal to 0 and take those values out. It kind of has the same ending effect. Well, just like equations, let's add 6. Let's divide by 2, and we get x cannot equal 3. And now I want to write that as an interval. So just for one quick example, I'm going to show you how this would work on a number line. I'm not going to do it on every single one. Normally when we're in person, I like using people to kind of come up to the front of the room. But let me draw this one out for you guys. Okay, so we have our function f of x equals 1 over 2x minus 6, and we say the domain is x cannot equal 3. However, we write domain as intervals, right? We've been talking about intervals for the last couple chapters. So how do we write that? Well, on a number line, right, these are all going to be x's. This is negative infinity to infinity. And we're saying we can be everything except 3. We don't want to be 3. Absolutely not 3. If you plug in 3, 2 times 3 is 6. 6 minus 6 is 0. So 3 is our only problem child, so to speak. However, just because 3 is a problem doesn't mean everything else is. We can be everything to the left of 3. We can also be everything to the right of 3. So here's how we write that. Everything to the left of 3 would be negative infinity up to 3, right? This says all the x values to the left of 3, with 3 not included because we're using parentheses. Okay? Well, we can also be everything to the right of 3, right? This was everything to the left of 3. This is everything to the right of 3, and that would be 3 to infinity. Again, 3 not included. So this right here would be the domain written in interval form. A good way of looking at this just says everything except 3. And that's all that's all it is, right? It excludes everything. Sorry, includes everything except 3, which is not included on either side of 3. So that's how domain's going to work. I'm going to come back and do like one example when we get to other cases, but in general, this is the thinking here. Okay, let's go back to the presentation. Okay, and we're back. And just to go over that again, we're saying everything to the left of 3, everything to the right of 3. All righty, 1 over 1 minus x squared. Well, we want to make sure that the denominator does not equal 0, right? That's our red flag here. Okay, 1 minus x squared cannot equal 0. Well, we can factor 1 minus x squared. We can set each factor equal to 0. So we can be everything except negative 1 and 1. Okay, well, think about this. We can be everything except negative 1 and 1. We can be everything to the left of negative 1. We can be everything in between negative 1 and 1. And we can be everything to the right of 1. So I'm not doing this one on the whiteboard, but I think you guys see, oh, we excluded negative 1. and we excluded positive 1. Everything to the left of 1, everything between -1 and 1, and everything to the right of 1. So, be very careful and kind of think about this. Look for this pattern that when we had one x value, that was a problem. We had 2 separated intervals. When we had 2 problem values, we had 3 separated intervals. So if you had 3 problem x values, what would the last one be? All right, how many intervals would that be? Alrighty, let's talk about square roots. Well, for square roots, we want to make sure that the inside is always 0 or bigger than 0. Case in point, we can be everything except negative numbers. Okay, so x plus 1 greater than or equal to 0. This ensures that everything we get on the inside is greater than or equal to 0. Well, subtract 1 on both sides, and wow, haven't we been writing intervals like this since like chapter P? This says everything to the right of 1 with -1 included. That's it. So stuff we were doing in chapter P, it's coming back. And that's sort of how this works for domain for square roots. Now, doing a whole bunch of examples, here we go. Find the domain of the 7th root of 400x squared minus 600x plus 800. Okay. But the rule we have for roots is for even roots. For even roots, for square roots, for 4th roots, for 6th roots. And 7th root is definitely not an 8th root. Sorry, 7th root is definitely not an even root. Think about when we were trying to evaluate odd roots versus even roots. We knew we can have negatives inside odd roots. You can take the 3rd root of -27, but you can't take the square root of -27. So because this is an odd root, the domain is all real numbers. Simple as that. Actually kind of nice. But now let's find the domain of the 6th root of x minus 12. Well, this is an even root, so we need to make sure everything on the inside is greater than or equal to 0. All right, x minus 12 greater than or equal to 0. Add 12. This says everything bigger than 12, so 12 to infinity. All righty, let's keep going. X minus 5 over square root of 3x minus 12. And here we have a square root, but it's in the denominator. So this was kind of like our 3rd red flag case. It's a combination of both those first 2 red flag cases with rationals and square roots. Normally, we're okay with our square root being 0 or positive. However, the second that square root or that even root is in the denominator, we're not allowed to let it be equal to 0 anymore. So instead of saying it can be 0 or bigger than 0, all we say is has to be bigger than 0, just greater than. Okay, well, we add 12, we divide by 3, all the x values bigger than 4, 4 to infinity, right? And specifically, we exclude 4 because if we had 4, 3 times 4 is 12, 12 minus 12 is 0, square root of 0 is 0. Oh, 0 in the denominator. So the only thing separating square roots in general versus square roots in the denominator is just whether or not we use a greater than or equal to sign. Okay. 15x squared plus 1 over square root of 2 minus x. Same thing. There's just a square in the denominator. We just want to make sure the inside is greater than 0. We don't want it to be equal to 0. It has to be strictly greater than 0. Alrighty, well, we can add x to... Okay, well, we can subtract 2 on both sides. We can divide both sides by -1, but think back to 1.6. When we divide both sides by -1, we flip the sign. Don't forget that. It's been a while, I understand, but divide both sides by -1, the sign flips to less than. This says all the x values less than 2, so everything to the left of 2. It's kind of weird to say that we can be, negative values for this, but think about what our square root is looking at, right? If x was -10, well, 2 minus -10 is 2 plus 10, and 2 plus 10 is 12. That's good for the denominator. But if you plugged in something like 3, 2 minus 3 is -1. Square root of -1 is complex. It's not a real number, so that wouldn't work. All right, one more case. In the event that you have a square root in the numerator and a denominator that separately causes a problem, what we're going to do is find the domains of each part separately and intersect them. So domain of the square root in the numerator, 0 is totally fine. So we have to make sure it's greater than or equal to 0. Subtract 2 and -2 to infinity. All right, we've done that before. But of the denominator, we want to make sure that the denominator does not equal 0. So x cannot equal 1. And that would be everything to the left of 1 with everything to the right of 1. And now what we're going to do is just intersect them. What does this interval and this interval have in common? Everything from -2 to 1 with 1 to infinity. So it has to be within these ranges. I know this extends all the way to -infinity, but let's plug in, say, -5. Well, -5 is okay for the denominator. -5 minus 1 is -6. That's good. But -5 plus 2 is -3. And we can't take square root of -3. So for square roots and denominators separately, take the domain of each part and intersect them. But this doesn't happen a ton. It does happen, but not a ton. Find the domain of 1 over 1 plus x squared. Oh, it's a fraction. Denominator cannot equal 0. 1 plus x squared can't equal 0. Let's subtract 1 on both sides. And you might think that you take the square root of both sides, square root of -1. Oh, that's not a real number. So there's no problem values. Every x squared is going to be not equal to -1. You can't square any number and have it be negative. So this is always true. Another way of thinking about this, there's always 3 types of numbers. There's negative numbers, positive numbers, and 0. Well, if we take a positive number and square it, it's positive. And then you add 1, and it's still positive. Well, we're looking for 0. Positive numbers are never 0. So this is good. Negative numbers, kind of similar, but you take a negative number and you square it, then it's positive. And then you just add 1 and you are still positive. So positive numbers aren't the problem. Negative numbers aren't the problem in this case. So it must be 0, right? Well, 0 squared is 0. 1 plus 0 is 1. And 1 doesn't equal 0 either. So all 3 types of numbers, positive, negative, and 0, don't actually cause any issues. Now, that's not a perfect way of thinking. It doesn't work nicely for all the other questions. But, if you get to a point where you're kind of like, what the heck is going on? There's pretty good rationalization for that. No pun intended with the rational. Okay, well, domain is the set of all x values that are included. So likewise, the range is the set of all y values that are included, or all the values that we can get by evaluating the function. Now, graphically, this is the set of all y values that appear in our graph. But it's kind of weird to solve for when it comes algebraically. Like graphically makes a lot of sense, no problems at all. But algebraically, it's very hard to determine range. Range is the set of all values that we get by evaluating the function. So are you going to evaluate the function at every x value in the domain just to see what y's you get? Absolutely not. So determining range algebraically, we're going to put on the back burner a little bit. We'll come back to that in 2.8 or 2.9. So some graphs. We've been doing a ton of graphing. And guess what? Graphing functions, no different than how we did it before. Plug in x and get a y or f of x value. So throw it back to 2.2 when we did like y equals x squared minus 3. You plug in x's, you get y's, table of values. It's no different, except now we're just using f of x's. So, but one thing that is interesting is that we can test to see if a graph represents a function. Well, that's called the vertical line test. Vertical line test says if your pencil or if your vertical finger, whatever it is, if it covers any 2 points at once on the graph of your equation, then the graph does not represent a function. Let's think back to that very first definition we came up with for functions. We said functions must use every x, but every x can only be used once. So if you have a vertical line and it covers a point here and a point here, it says that that same x value is going to two separate y values, and that violates the second rule of functions. So vertical line test says if your finger covers 2 points at once vertically, right? Your vertical finger covers 2 points at once, it is not a function. Okay, finger, pencil, whatever works for you, right? And we can get some information about a function by looking at its graph. For example, if AB is a coordinate point on the graph, then A is in the domain, B is in the range, and B is the value at A. But these are things that we already knew. Domain would be the set of all x values that you see, all the x values that are included. And like I said, range, not so bad to find graphically. It's the set of all y values that are included. So let's take this graph right here, and we want to find domain, range, and determine whether or not it's a function. Well, domain, set of all x values that are included. And how we read domain is left to right. Look at some of those domain examples. It was always furthest left we could go to furthest right we can go. So to find domain, we're going to follow this graph left to right and see what x values and y values are included. Y's will be, vertical. But let's all see all the x values we get. Well, this arrow tells us that we go forever down and forever to the left. So even though we don't see it on this specific picture, it does say by this arrow that it's defined for every value to the left of where this is pointing, right? Arrow says forever down, forever left. So we know this is defined for everything from negative infinity. So we're at negative infinity, we follow the graph, and we just want to see how far right we can go. Well, we can go up and down and left and right, and this goes forever up and forever to the right. So our domain is negative infinity to infinity. Even though we don't actually see every single value on here, this says that it is extending forever to the left and forever to the right. Range, similar, except when we read domain, we read left to right because x's run left to right, negative to positive. But y doesn't work the exact same way. Y running negative to positive is going down to up. Ooh, that's kind of weird. So range, instead of reading left to right or up and down, what we're going to do is read down to up. How far down can we go to how far up can we go? All right, how far down does this graph go? Oh, well, it's a little clear that this goes all the way down to negative infinity. But how far up does it go? It goes up, and it comes back down, and it goes back up, and it goes up forever. So that's also negative infinity to infinity. Last but not least, is this a function? Vertical line test says, if our finger covers any 2 points at once, it is not a function. So I know that this, my little cursor here is not a nice long vertical line, but you should do it, follow along with your pencil, and see that at no point does your pencil cover more than 1 point at a time. Since it never covers more than 1 point at a time, it is a function. It's a problem when you do cover 2 points at once. Okay, similarly, let's do this for a circle. We already have an answer to the function part, but let's still take some information. Domain, set of all x values that are defined. So we're going to go left to right, see how far left and right we can go. Well, we see that the first x value that is defined, that has a value, is -3. Now let's follow the graph left to right. Everything between -3 and 3 are defined. Notice -4 isn't defined. There's no value here. 4 isn't defined either. The only values for which this graph has value, only x values for which this graph is defined is from -3 to 3. -3 and 3 included. Similarly, for range for the y values, the furthest down we can go is -3. Furthest up we can go is +3. So that's not so bad. However, bigger question, is this a function? And the answer is no. Take your pencil, cover this line right here. Do you notice that your pencil covers this point right here and this point right here? Oh, well, your pencil covers 2 points at once. That's the definition of not a function. It fails the vertical line test. We could say this one passes the vertical line test. This would be fails the vertical line test. Okay, so with that said, that's the end of 2.4. 2.4 really sets the stage for functions, but 2.5, we're going to get back to looking at some of the properties of functions. So I will see you in 2.5. Bye. Hi, everyone. Welcome back to 2.5. In 2.4, we introduced functions for the very first time, and now we're just going to look at some odds and ends properties of functions, so to speak. So the first two, very interconnected. Third one, similar to something we've done before, last subsection, those other properties, kind of weird looking things, one really nice, one not so nice. But let's get right into it. So increasing and decreasing. Your function is said to be increasing if your y values increase over some interval x1, x2. So if your ending y value is greater than your beginning y value, then your function is increasing on the interval x1, x2. Likewise, we say your function is decreasing if the y values go down on an interval x1 to x2. We say a function is constant if the y values remain the same. But one thing I want to stress here is that we are talking about intervals. Our answers for increasing, decreasing, and constant are intervals of x's. What we're trying to do is say, on these x values, we're describing what is happening for y's. On this set of x values, the y values are decreasing. On this set of x values, the y values are increasing. We're not saying how much they increase. We're not saying how much they decrease. We're just saying from x equals 1 to x equals 2, we are increasing. You can kind of think about it like this too. Let's say you are driving in your car. At time 30 seconds, you are increasing your speed. So from time equals 30 seconds to time equals 40 seconds, you are increasing your speed. We didn't say how much your speed increased by. We just said on that 10-second interval of time, your speed went up. Now let's say you hit the brakes at time 90 seconds, and then at time 100 seconds, your speed is lower. So from the interval 90 to 100 seconds, your speed went down. Your speed decreased. Or you can also say your speed remained constant from time equals 2 minutes to time equals 3 minutes. Let's say if you're in like cruise control or something. So we're not talking about the y values. We're talking about the x values. Our answers are going to be in terms of x, but those x values are going to describe what the y's are doing. Okay, here we go. So let's say we have a graph like this. It extends forever in both directions. I just didn't put the arrows, but that's okay. So notice that things are a little different around these points. What I mean by that is let's follow the graph. Okay, on this graph, well, if we follow it, we are literally going up. So we are increasing up to the point -1, 2. So what this says is this: from x equals -infinity to x equals -1, the y values are increasing. So we say from -infinity to -1, again, these are x values, not y values. I don't care what the y values are. I only care on what interval of x's your function is increasing. So on this first interval, again, I don't care how high it increased. I don't care what it got up to. I just care that on this subset of x's, the y values went up. Okay. But at -1, something changes. We stop increasing and we start decreasing. We start going down. So we know we're increasing from -infinity to -1, but on the x values, -1 to 1, the function is decreasing. Again, no y values included. We're saying from x equals -1 to x equals 1, the function is decreasing. The y values are decreasing. Don't care what the y values are, only care to describe what they are doing. Last but not least, -1 to 1, we decrease, but at x equals 1, we change to increasing one more time. So notice this is an interval of x values. This is an interval of x values. This is an interval of x values. At no point do we use the y values. We are only describing what the y values are doing with some set of x's. That's really, really important. Now, in total, we like to write our answers as increasing all the increasing intervals together. So -infinity to -1, union 1 to infinity. Likewise, decreasing, well, we only had one decreasing interval, so there we go. We like to write our answers as all the increasing ones, all the decreasing ones. However, it's easier for me if I just, show them to you one by one. But this is how we would formally write our answer. But on each individual interval, here's our answers. Again, sets of x's to describe what the y's are doing. Also, I want to stress that for increasing, decreasing, we're always going to use parentheses. It isn't quite clear. For example, at x equals 1, are we technically decreasing or are we increasing at x equals 1 specifically? Well, it's kind of a hard question to answer because the decreasing ends and the increasing starts. So instead of trying to say like, oh, well, it's decreasing on this part or it's increasing on this part, we're just always going to use parentheses for when it comes to increasing, decreasing. So this is not a coordinate point. It is an open interval. I know this is like the one time that we're really using similar notation for different things. Bear with me. All right, let's do another one. Here, let's start from the left of our graph and just follow along and see what happens. Okay, well, we start up here, and you'll notice that we are going down. So from -infinity to x equals -1, our y values are decreasing. From -infinity to x equals -1, the y values go down, so we are decreasing. But then at -1, we change. So from -1 to 0, we increase. From 0 to 1, we decrease. And last but not least, from 1 to infinity, we increase. So again, we do not care what the y values are. We only care what x values, for what set of x values do the y values increase and decrease. Notice we have this to say, oh, on this set of x's, the y values went down. On this set of x's, the y values went up. That's our goal here. Not including y values, only including x values each and every time. Okay, so in total, we like to write our answer all the decreasing and increasing intervals together. So we are increasing from -1 to 0, union 1 to infinity, and decreasing from -infinity to -1 and 0, 1, with a union 0, 1. Okay. So that's increasing, decreasing. I think you guys get the idea. It's just got to be really careful because again, you're going to be so tempted to use the y values, but that's not what we're doing. We're using sets of x values. Just read left to right. From this x to this x, did we go up or down? From this x to this x, did we go up or down? That's what increasing decreasing is. Now, extrema is a really fancy word for maximums and minimums. So technically, maximums isn't grammatically correct. It's technically maxima. However, I am very conditioned to say maximums and minimums instead of extrema or maxima and minima. Also, my name may or may not be Max. So in a lot of cases, I say maxes and mins. I don't even say maximums and minimums. So fancy phrasing. All it is this. Maximums occur when your function changes from increasing to decreasing. Think about what happens when your function changes. Let's say you're increasing, and then at some point you start to come back down. Well, that location at where it stopped increasing and started decreasing, that location at the top represents kind of a maximum value. Around that point, nothing is bigger than it. It might get bigger than it, down the road. That's where we get into different phraseology of what types of maximums. But where we change from increasing to decreasing, we call that a maximum. Likewise, we use minimums to say decreasing to increasing at the location that we change from decreasing to increasing. That is a minimum. So, big so here. The big difference from increasing, decreasing, and maxima and minima is that increasing, decreasing are intervals that describe what happens to the y's. But extrema, maximums, and minimums are specific locations in time or in space. Notice, we'll go back to this example. We're going to come back to this example in just a moment. But the increasing, decreasing were intervals, these long, smooth intervals of time where we were decreasing and then increasing and then decreasing and then increasing. But at the locations where it changes, those are maximums and minimums. So increasing, decreasing are intervals. Extrema are points. So if your function does not change, well, nothing happens. I want to stress that maximums and minimums only occur when we change between increasing to decreasing or decreasing to increasing. So if your function doesn't change at some specific value, there is no maximum or minimum. What sometimes happens is you'll be increasing and then you kind of plateau, but then you increase again. In the event that you change from increasing to constant to increasing again, well, we didn't change specifically from increasing to decreasing. Maximums only occur when you change from increasing to decreasing, not increasing to constant, not decreasing to constant, only increasing to decreasing or decreasing to increasing. If it doesn't change in those only two scenarios, we don't call it anything. You might actually call something like this plateau a shelf, but that's not really important right now. How we phrase this is the extremum occurs at the x value, with the maximum or minimum being the value itself, being the y value itself. So let's go back to this example. We said we increased, and then at -1, we started decreasing. Well, we call x equals -1 a maximum. It changes from increasing to decreasing. Notice at the points right around it, there's nothing bigger than it. So this is a maximum. So there is a maximum at x equals -1 with a value of 2. Finally, we're using the y values. There's a maximum at x equals -1 with a value of 2. Okay, similarly, we are decreasing, and then at x equals 1, we change to increasing. Well, decreasing to increasing is the definition of a minimum. Okay, so there is a minimum at x equals 1 with a value of -2. And that's how we would formally write this. As you go along, it's totally fine to write maximum, with the coordinate point -1, 2. But as we're learning this for the first time formally, I want to make sure it's very clear what these things mean. Okay, let's go back to the second example again. We are decreasing from -infinity to -1, and then at -1 we change to increasing. Decreasing to increasing is a minimum. So there is a minimum at x equals -1 with a value of 1. Then we start increasing, and then at x equals 0, we decrease. So there is a maximum, right? Increasing to decreasing is a maximum. There is a maximum at x equals 0 with a value of 2. And last but not least, I don't think I need to go back, but there is a minimum at x equals 1 with a value of 1. So only maximums and minimums, they only occur when you change from increasing to decreasing or decreasing to increasing, respectively. Constant doesn't happen anywhere in that definition. Staying constant, like increasing to increasing, also does not change there. So please don't use maximums and minimums for any other situation than those two changes. Okay, so a lot going on in those two, but let's talk about even and odd. And this is something we've actually kind of talked about before. We describe a function to be even if f of -x equals f of x. Plugging in -x wherever we see x, that sounds something really familiar. It sounds like symmetry. So even functions, if you replace -x with x, are symmetric about the y-axis. So for example, f of x equals x squared is even, not necessarily because it has an even exponent, but if you plug in -x wherever you see x, well, you would have -x squared, and -x squared is then positive x squared after simplification. So because f of x is the same as f of -x, right? They both equal -2. They both equal x squared. In that case, this is an even function. Okay, so a function is odd if when you plug in -x, you get the negative version of your function. Ooh, that's kind of weird. So odd functions are symmetric about the origin. And for example, x cubed is odd because when you plug in -x, well, -x cubed is -x cubed. Okay, well, if we regroup this to say -x cubed, well, x cubed is the original function. So this would be negative f of x. F of -x equals negative f of x. This is symmetric about the origin, but we also call it odd. If you plug in -x and you don't get either situation, that's totally fine. It just means your function is neither. That happens plenty of times. I also want to stress that we have symmetry about the y-axis and symmetry about the origin, but no symmetry over the x-axis. Well, let's say we have a graph that looks like this. Well, here's the x-axis, so this would be symmetric over the x-axis, but 2.4 is screaming. This doesn't pass the vertical line test. Maybe over here. Yeah, there we go. Sorry. I didn't expect to really be using my hands for this, but vertical line test. It crosses 2 points at once. Functions that are symmetric over the x-axis aren't functions to begin with. So we don't even need to talk about symmetry over the x-axis. Okay. Is this function even, odd, or neither? Let's see. Well, when we were looking for symmetry over the x-axis, y-axis, or origin, we had a specific method as to how we did it. Y-axis replace x with -x. X-axis replace y with -y. But doing even and odd, it's actually pretty nice. For all of these examples, go right for plugging in -x, right? Notice f of -x, f of -x. Just go right for plugging in -x for x. That's how we'll start doing even and odd. Okay, -x cubed is negative x cubed. Negative 4 times negative x is positive 4x. Now, this is really similar to what we started with. Well, x cubed became negative x cubed, and negative 4x became positive 4x. Well, if we want to get the original coefficients, why don't we factor out a negative 1? Well, if we factor out a negative 1 from both, ooh, look at this. This, x cubed minus 4x, x cubed minus 4x. This part inside the parentheses is exactly f of x. However, it's not perfectly f of x because we have a negative sign on the outside. Well, if f of negative x equals negative f of x, this is the definition of an odd function. So the conclusion here, f of negative x led us to negative f of x. That is the definition of an odd function right there. Okay, let's do another one. F of x equals x to the 10th plus x to the 6th plus 5. Wherever we see x, let's plug in negative x. Well, negative numbers raised to even powers are positive. Negative numbers raised to even powers are positive. Oh, well, actually, this is pretty quick. This is exactly like the other one. So f of negative x gave us exactly f of x. F of negative x equaled, after simplification, f of x. That's the definition of an even function. Okay. Well, you might be thinking, well, this example had all odd coefficients, all odd degrees. So it was odd. And this one had all even degrees. So this must be even. But what if we have both? Well, maybe you have an idea on that answer, but wait till you see the next example. All right, same thing. Let's go in for plugging in negative x. Negative x cubed is negative x cubed, so this will be negative 2x cubed. Negative x squared is then positive x squared. And notice that we can't treat this like the odd example. Here we have 2x cubed, and this is negative 2x cubed. So it would be nice if we pulled out a negative 1, but here we have positive x squared, and the same thing again. If we pull out a negative 1 to change negative 2 back to 2, well, then we would be changing x squared to negative x squared, and that's not what we want. That would be going backwards. There's nothing we can do to manipulate this to look exactly like the original function. In that case, if there's nothing we can do, it's neither. Okay, well, so even exponents, it's even. Odd exponents, it's odd. Both exponents, both even and odd, it's neither. Well, how about this one? Here we have 2 even exponents in the numerator and 2 odd exponents in the denominator. It must be neither, right? Let's see what happens. Let's plug in negative x. So 3 times negative x to the 4th minus 5 times negative x squared. 4 times negative x to the 5th minus 2 times negative x cubed. Well, negative raised to even is positive. Negative raised to even is positive. Down here, negative raised to odd is negative. Negative raised to odd is negative. Well, negative is positive. Okay, well, the numerators are identical. 3x to the 4th minus 5x squared, exactly what we started with. But the denominators are off by a factor of negative 1. Positive 4x to the 5th, negative 4x to the 5th, minus 2x cubed, positive 2x cubed. So what if we factor out a negative 1 from the denominator? Well, we saw a couple times that if the denominator is negative, this technically means the whole thing is negative, right? If you were to redistribute this negative, you wouldn't distribute it to the numerator and the denominator. You would only distribute it to the to one or the other. Well, this, what is now inside the parentheses, is exactly the original function. Well, f of negative x equals negative f of x is the definition of an odd function. So, you can be easily fooled by degrees and exponents, so be very careful with that. It's just something that happens. That brings us to our last 2 properties of 2.5, things that are very different from the a couple of things that we've talked about so far. Increasing, decreasing, extrema, and to an extent, even an odd are very graph heavy, but these next two, not quite. So average rate of change, you guessed it, literally the average rate of change your function changes over some time period. So if you were to graph this, I know it said not as graphic, but you're going to spend way more time doing this algebraically. Graphically, if you were to draw the slope of the line in between 2 points, that slope would be the average rate of change, right? You have some function over some very specific time interval. So from some very defined x to some very defined y. If you have those 2 points and you draw a line between them, the slope of that line is the average rate of change. So for some interval, x equals a to x equals b, the average rate of change is f of b, the value at b, minus f of a, the value at a, over b minus a. This looks a lot like y2 minus y1 over x2 minus x1, but now we have a very specific name. But also, when we talked about slope the first time, it was specifically for drawing lines. We're saying, what is the average rate at which your function changed over some time period, right? Your function can go up and down like crazy, but what's the average rate at which it changed? And that's what average rate of change gives us. Also, I might say AROC a couple times. It's a nice way of simplifying it. All right, so find the average rate of change from f of x equals 2 minus 3x squared from x equals 1 to x equals 3. In my opinion, it is probably in your best interest to solve for f of a and f of b first. A and b are always the beginning and endpoints of your interval. This is from 1 to 3, so a equals 1, b equals 3. There's nothing really surprising going on there. But instead of, trying to plug everything in to the average rate of change formula at once, do it in pieces, right? It ain't going to hurt you. Do f of a, where you solve the function with a plugged in, or more specifically 1 in this case. So 2 minus 3 times 1 squared. 1 squared is 1. 3 times 1 is 3. Negative 1. And take the time to do it for b as well. 3 squared is 9. 3 times 9 is 27. 2 minus 27 is negative 25. So take the time to do that. Don't try and plug it all into the AROC formula right away. Okay, well, average rate of change, f of b minus f of a over b minus a. Well, we just found f of b, and we just found f of a, and b is 3, and a is 1. So that's actually pretty nice. We already have everything. Negative 25 minus negative 1, that's plus negative 12. So the average rate at which our function changes from 1 to 3 is negative 12. If you were to draw a line from 1, negative 1 to 3, negative 25, its slope would be negative 12. Let's do that again. X cubed plus 1 from x equals negative 2 to x equals 4. Well, we start from a, end at b. So a is negative 2, b is 4. Let's find f of a, f of negative 2, by plugging in negative 2 to the function. Negative 2 cubed is negative 8. Negative 8 plus 1 is negative 7. F of b says plug in b, plug in the final endpoint. Well, 4 cubed is 64. 64 plus 1 is 65. F of b minus f of a over b minus a. Well, we got f of b right here. We got f of a right here. And we have a and b right here as well. Bunch of minus minus plus 72 divided by 6 is 12. Average rate of change. Not anything super crazy. But that brings us to our very last property for 2.5, and that is the difference quotient. So its meaning is kind of crazy because we haven't spent a whole lot of time talking about this, but difference quotient is a method to find the formula for the slope of the tangent line at any point on the graph. So imagine you have some curve and you want to find a tangent line to any point on that curve. So let's say tangent lines in general, let's say you have a graph that goes like this and it comes down. But what if instead of coming down, we wanted to draw a line at the point where it is still going up? We draw a line tangent to the graph. Kind of difficult to explain. Actually, you know what? I'm going to take a second and show you what this looks like. What would a presentation be without a single thing on the whiteboard? So let's say you had some graph that looks like this. If you wanted to draw a tangent line, so a tangent line would be a line that kind of like touches at one specific x value and goes in the direction that it was heading. So at this point, tangent line runs like this, but down here, tangent line would run like this. So imagine like you're throwing a baseball, and when you throw a baseball, when you let go, the ball travels in the position that you were letting go, or in the direction of where you would have let go. If you let go of the ball too late, you throw it to the ground. If you let go of the ball too early, it goes up in the air. But if you try and throw it straight, you have to throw it at a very specific time. So that's what tangent lines are. I realized in a digital setting, not as easy to describe, but that's what tangent lines are. So what the difference quotient is doing is getting us a formula for the slope of that tangent line at any point on the graph. So difference quotient is given by this. Oh, didn't I say this thing was going to come back from 2.4? Sure is. Difference quotient needs f of x plus h. All this is the function with x plus h plugged in, the original function, and h is going to be just some constant that we don't know. So let's find the difference quotient for 2x squared minus 3x plus 5. We need f of x, we need f of x plus h, and we need h. Well, h is just h, and f of x is sitting right there for us. So all we need is f of x plus h. This says wherever we see x, plug in x plus h. All right, here we're going to have to FOIL. Here we're going to have to distribute. Here we're going to have to distribute 2. So I know I skipped through a lot of that, but we've been doing this stuff since like chapter P. It's just a matter of, this is the new step of plugging in x plus h wherever we see x. So this is all of f of x plus h. And we want to plug this into f of x plus h. And we want to plug this in for f of x. So taking f of x plus h, taking f of x, and plugging them both in, we get this ugly monstrosity. So here, let's distribute our negative sign, right? Plugging in f of x, use parentheses. Let's distribute the negative sign. And now, you think it doesn't get any better, but it actually does. 2x squared minus 2x squared. Oh, that goes away. Minus 3x and plus 3x. Oh, that goes away too. And positive 5 and negative 5. Well, out of 9 terms that we have here, 6 of them just canceled out. 2x squared minus 3x plus 5. Well, minus 2x squared plus 3x minus 5 canceled out all of those terms. And we're left with these 3. Now, we're almost there, but notice this. Every term in the numerator has an h. So let's factor out h. And if we have h times something divided by h, we can cancel those h's out. And we're left with just 4x plus 2h minus 3. Now, we are not even close to Calculus 1 just yet. That is coming in, 2 courses if I ever make those videos. But this is one step away from being the first derivative. So that's actually a very interesting piece of information that we get. So that's the difference quotient. Like I said, it's a Calculus 1 thing, but notice that there was nothing here that we weren't capable of doing already. So that's difference quotient. Weird, very strenuous algebraic activity. This was kind of a decent amount of work for not a very exciting final answer, but we can get them to look really, really ugly. Let's do one more. That's just a polynomial, but we'll call it after that. So difference quotient, we need f of x, we need f of x plus h, we need h. H is just h, f of x is just itself. but we need f of x plus h. Wherever we see x, plug in x plus h. We're going to FOIL x plus h squared. We're going to distribute this outer negative sign. And now all of this information, f of x plus h and f of x, are going to go into the difference quotient. Alrighty, how beautiful. Let's distribute a negative sign to each term in here. And we see negative x squared cancels out with positive x squared. Positive x cancels out with negative x. And negative 3 cancels out with positive 3. All of these terms in the numerator have an h. Let's factor out h. H then cancels out. If you did this right, you should have something like this that happens, and you're left with negative 2x minus h plus 1. And that's the end of 2.5. So some very interesting properties, right? Increasing, decreasing, and maximums and minimums, kind of along with difference quotient, is something you will study very in depth in Calc 1. But even odd, it's kind of just an extension of symmetry we talked about in 2.2. So that's the end of 2.5. We're going to change gears a little bit in 2.6 and talk more about graphs of functions, very specific graphs of functions, but not really a ton of new information there, just looking at some of the weird types of functions that we actually have. So with that said, I will see you in 2.6. Bye. Hi, everyone. Welcome back to 2.6. Here in 2.6, we're just going to kind of look at some graphs of functions. Literally, it's called a library of functions. All the things that we've talked about so far, just looking at what their graphs would look like, because knowing what their graphs would look like are going to help us into the next section when it comes to transformations. But for now, let's just build our way up to what do graphs of different functions look like. Let's build a library of very basic functions. So we'll start with linear functions. Well, lines are graphs of the form y equals mx plus b. So linear functions, believe it or not, are functions of the form f of x equals mx plus b. No different, except now that we have introduced function notation, we are allowed to use f of x in terms of, instead of y, I should say. So f of x equals mx plus b is a line with some slope. That's not really surprising to us. F of x equals b, where there is no slope, or the slope is 0, I should say. We call that the constant function, because no matter what you plug in for x, you're always going to get that value b, the y-intercept. F of x equals x, we refer to as the identity function, because no matter what you plug in for x, that's what you will get back for f of x. So for example, if you plug in x equals 1, well, then f of 1 equals 1. You plug in negative 5, well, f of negative 5 equals negative 5. So it's the identity function. The domain of all linear functions, right, going back to 2.4 a little bit, the domain of all linear functions is all real numbers. There's nothing you can plug in that will make a line undefined, but the only thing that could be different is the range. Range is normally when there's a slope, negative infinity to infinity, but when it comes to constant functions, it's just whatever that y-intercept is. That's the only y value you can get. So here's some sloped lines. Not really surprising. We spent an entire section talking about lines. There's the identity function. There's the constant function. Not so scary. But only difference now is that instead of giving you 2 coordinate points, I can instead give you function notation for values, and you write a line based on that. Given that f of 1 equals 4 and f of negative 3 equals negative 2, write the function of a line. And guess what? This isn't really that scary. So if f of 1 equals 4, this is saying at x equals 1, the y value is 4. At x equals negative 3, the y value is negative 2. Well, that's the definition of 1, 4, and negative 3, negative 2, right? If x is 1, the value is 4. If x is 1, y is 4. Yeah, wow, that's just the point. Well, from here, this is exactly like we built lines for graphs, except it's going to be one extra step. First step, we got to find the slope, plug in everything we know. Negative 6 over negative 4 is 3 over 2. Y equals mx plus b. All right, well, we know the slope is 3/2. Let's plug in either one of our 2 points. It doesn't matter. I'm going to plug in 1, 4. So x is 1, f of x is 4, right? F of x and y are interchangeable, so that's not super scary. Well, from here, subtract 3/2 on both sides. We can do fraction subtraction. B is 5/2. So if we were writing the equation of a line, we would write y equals 3/2 x plus 5/2. But if we are writing the function notation for this line, it would be f of x equals 3/2 x plus 5/2. But the line itself, no different from stuff we've talked about before. One more example. If we have f of -2 equals 2 and f of 1 equals 8, well, this says at x equals -2, y equals 2. At x equals 1, y is 8. Oh, how nice. Alrighty, plug in everything we know to find the slope. We get 2. Yeah, this isn't scary at all. I think it's very familiar to us. So y equals mx plus b, and we just found to be 2. Plug in either point. I'm going to plug in 1, 8. Again, it doesn't matter which point you plug in, you will get the exact same answer. We saw that when it came to lines. All right, well, 2 times 1 is 2. Subtract 2 on both sides, we get 6. So y equals 2x plus 6, but in function notation, f of x equals 2x plus 6. Okay, linear functions, not really any new information, except we have one step in the beginning that makes us write what the points are, and we have one step at the end, just instead of saying y equals, we have f of x equals. Also, you could have just started with f of x in the beginning, but, you know. All right, root functions. So we've looked at roots before, but we don't really know what their graphs look like. They're actually kind of funky looking. But to do root functions, what we're going to do is just a table of values. So let's plug in 0 to square root of x. Well, square root of 0 is just 0. So that point is 0, 0. 1, well, square root of 1 is 1. So that point is 1, 1. And now you could go up to 2, but square root of 2 isn't a nice number. That's not an easy number to graph. Instead, why don't we jump up to 4? Okay, well, square root of 4 is just 2. So we get 4, 2. Well, the next value would be 5, but 5 doesn't work nice. So how about 9? Okay, square root of 9 is 3. So that point is 9, 3. Let's do 16. Square root of 16 is 4. So we get 16, 4. So I mentioned it way back when we started graphing in 2.2 that you could use a disjoint set of x values to plug in. At the end, you're going to connect all of them anyway. So, using 0, 1, 4, 9, 16 is to our advantage because not so scary to plug those values into square roots. The second you try and use 2 or 5 or anything like that, you might be in trouble. So here's what happens when we graph those points and connect them. We get something that looks like this. And that makes sense because we can't take square roots of negative numbers, so there's nothing to the side. Square roots can't produce negative numbers, so there's nothing below the x-axis. So, yeah, this is what square root functions are going to look like, and this is what all even root functions are going to look like. So this is square root of x, but fourth root of x would be just this graph, but a little bit growing. It would grow a little bit slower. Sixth root, grow even slower than that. So the shape will not change, just a matter of the rate at which it grows a lot slower. Okay, well, let's do cube root. And cube root, we have a lot more values available to us. So let's plug in -27 because we can take the cube root of -27. That's -3, right? Even roots, square roots, we can't plug in negative numbers, but odd roots, we can. Okay, well, yeah, there we go. -8, cube root of -8 is -2. So -8, -2. -1, cube root of -1 is -1. -1, -1. Cube root of 0 is just 0, so there's 0, 0. And I think the last couple points are self-explanatory. So again, we want to choose points that are to our advantage. So for example, plugging in -27 and then jumping up to -8, that helps because we don't know any of the cube root values in between them without getting some really ugly numbers. So again, it's okay to be picky and choosy the values you plug in. And notice that the cube root function has a similar shape to the square root function, right? This right here kind of looks like the square root part, but now we get a part to the left of the y-axis because we're allowed to plug in negative numbers. So square roots and all even root functions, their domains are 0 to infinity with 0 included. The range, also 0 to infinity, right? Square roots, even roots. We can't plug in negative numbers. We can't get negative numbers out. But cube roots and all other odd root functions, also going back to that cube root picture, 5th root, 7th root, 9th root, as you go up higher in the root, the graph just grows less drastically in both directions. So domain for those, all real numbers, and range, all real numbers, because we can get anything we want out of both. So not really anything surprising so far, but we have to introduce one new type of function, piecewise functions. So kind of fancy looking here. So piecewise functions are functions made up of smaller functions over smaller intervals. So this is very scary looking notation, but all this says is that for some interval of x, let's say x1 to x2, you're going to use one function f1 of x. But on a different interval of x, you will use a different function. On a third interval of x, you will use a third function, and so on, as many as you want. Now, the higher up in number you go, the uglier it gets, right? It becomes kind of unnecessary as time goes on. But we're going to look at some examples with 2 parts and 3 parts. So, but you could really go 4 or 5, but at that point, it's just getting messy for no reason. So the x values in which we change, right? Notice this interval is from some x1 to x2, but at x2, this changes here. At x3, this interval ends and this interval starts. So the location at which these functions change and you jump between which one you use, we call those transition points. And transition points are unique because what we're going to need to do is graph our function at every transition point twice. So here's what happens. Well, actually, before we do that, let's just practice how we evaluate these things. So let's find f of 0 and f of 2. So if you want to evaluate, say, f of 0 for a piecewise function, your first step is to look at the intervals. Piecewise functions say if x falls into this interval, you're going to plug it into this corresponding part of the piecewise function. So for example, 0 is less than 1. So we would plug 0 into this first part. Okay, so it would go into x squared, which would just be 0. Notice that 0 is not greater than or equal to 1. So we wouldn't plug 0 into the bottom one. We would only plug 0 into the top one because 0 is less than 1. Likewise, 2 is not less than 1, but 2 is greater than or equal to 1. So when we go to plug in 2, we would plug it into the second one. Okay, and simplifying that, not really anything crazy. But again, figure out where that x value belongs before you start to plug it in. Okay, so going back to the transition point thing, see here that at x equals 1, we stop using this top function and we start using this bottom function. However, if we're doing a table of values like -3 to 3, you're going to be compelled to stop plugging this in at 0. But don't forget, all the values less than 1 is not just 0. Another value less than 1 is 0.5, 0.75, 0.9, 0.99, 0.999. We can plug all these values that are extremely close to 1, but values that you would miss out if you stopped plugging in at 0. So here's what we're going to do. Well, let's do -3 to 3, and let's just go down the order until we get to 1. All right. Well, -3 is less than 1, so we'll plug -3 into the first part. -3 squared is 9, so our point is -3,9. -2, well, -2 is still less than -1, so we're still going to plug it into the top. -1, still less than 1, we're going to plug it into the top. 0 is less than 1, so we're still going to plug it into the top. But then at 1, well, if we wanted to plug in x equals 1, x equals 1 fits into this bottom interval, not the top interval anymore. However, if you stop graphing this part of the function, if you stop graphing the x squared part of the piecewise function at x equals 0, you miss out on all of those intermediate values between 0 and 1. You miss out on graphing 0.5. You miss out on graphing 0.99. So to calm that fear, what we're going to do instead is we're going to plug that transition point x equals 1 into the top. It doesn't belong there. I totally get it. But what we're going to do instead is when we plug 1 into the first part of the function where it doesn't belong, what we're going to use instead is an open circle. So we're going to use some asterisks here to denote this is going to be an open circle, right? 1 should not be getting plugged in to this top one. However, what we're going to do is graph that point 1, 1, so we connect all 5 of these x squared points together, but instead of saying there is a value at 1, we're just going to put an open circle there. And you're going to see how this works when we actually go to graph. Okay, well, at x equals 1 really belongs in here. So when we go to actually plug x equals 1 in, we're going to plug it into the bottom function. All right. And then you want to plug in 2. That's going to go in the top function, the bottom function as well. You want to plug in x equals 3, you're going to plug it into the bottom function as well. So to graph piecewise functions, you're going to graph each of these sets of points together. And what I mean by sets is the set of points that all use the same function. So for example, these first 5 points all used x squared. So we're going to graph all of those x squared points and connect those x squared points. Then separately, we're going to graph the 2x plus 1 points and connect the 2x plus 1 points separately. So graphing the x squared points, then graphing the 2x plus 1 points. And now here's why it was important for us to graph our transition point twice. Notice that at x equals 1, well, this was, x equals 1 belonged in the top, but how do we not graph this part into the first part of the piecewise function? If we didn't graph 1, 1 with an open circle here, we would have just gotten the little branch right here. We would have completely missed out on this tiny little area between 0 and 1, right? We had to do that because if you want 0.5, 0.5 belongs in the x squared part, right? 0.5 was less than 1. So if you don't graph transition points like this, you're going to miss out on all of those points that are in between, kind of in flux around your transition point. So, if you had graphed just this part and just this part, you would see that you would have literally a gap in your graph. So just be sure to graph transition points twice and try and figure out which part of the piecewise function does it go into. Okay, let's do the same thing. Let's do a slightly different function here. Let's do x squared, but x is less than or equal to -1, 2x, x is greater than -1, and notice this time, transition point is going to be -1. Okay, well, let's do -3. -3 is less than or equal to -1, so goes into the top. -2, -2 is still less than or equal to -1, so it still belongs in the top. And now let's think about our transition point again. Here's the weird part. In the last question, x equals 1 didn't belong in the top because the interval in the first question was x is just less than 1. But this time, we have x is less than or equal to -1. Well, -1 actually belongs in this part of the piecewise function. So we don't always graph an open circle the first time we see a transition point. We need to graph an open circle at the place it doesn't belong. Well, -1 belongs in x is less than or equal to -1, and -1 does not belong in x is greater than -1. So the open circle part comes the second time around because of the greater than. So -1 does belong in the top, and we get that point, but -1 doesn't belong in the bottom. So we're going to plug -1 into the bottom, but this part is going to have an open circle. Okay, well, from here, we kind of see that as soon as we start using the next part of the function, it just stays that way. So, right, 0 is greater than -1, so it's 2 times 0. 1 is greater than -1, so that'll be in the bottom part as well. And 2 and 3. So again, what we're going to do is graph all the points that use the same part of the piecewise. These 3 points use the x squared, so we're going to graph those together and combine those. And these all used the 2x part, and we're going to graph those and combine those. There's the x squared part, there's the 2x part. And notice, right, -1 was our transition. If we only started graphing the 2x part at 0, because 0 is greater than -1, we would have missed out on this little branch right here. So please be very careful. Let's do, I think, one more example. Here, 2 is our transition point, but notice the first time we see 2, it will not belong there. So we're going to graph an open circle at the first time we see the transition point, right? Last one, we had x is less than or equal to -1. This time we have x is less than 2. So, right, open circle here, closed circle here. Well, I think plugging in the points, not so scary anymore. -2, -2 is less than 2, goes at the top. -1, still less than 2, goes in the top. 0, less than 2, still goes in the top. 1, less than 2, still goes in the top. But 2, right, 2 technically doesn't belong in here. So we need to graph an open circle into this part of the function. But then when we actually go to graph 2, it'll belong in the bottom. So 3 times 2 plus 1 is 7. 3 times 2 is 6. 6 plus 1 is 7. And now from here, we're just going to use second part of the piecewise over and over and over again. Okay, graph these parts because these all use -2x plus 1, and then graph these parts because they use 3x plus 1 and connect them separately. So again, had you stopped graphing the top part of the function at x equals 1, you would have missed out on this tiny little branch right here. That's very important. Okay, very last part of 2.6, just looking at graphs of functions, just so we have a baseline as to what they look like. Squaring function, x squared, parabolas. We'll spend a little bit more time with this in the next chapter, but not such a scary looking picture. X cubed, cube root, kind of weird looking, but yeah, there we go. Absolute value function, absolute value of x. Reciprocal function, 1 over x, this funky looking behavior. Maybe we look at something like this in the next chapter too. 1 over x squared, similar, except if we're squaring every value, no value will be negative. Rational powers, if the denominator is even, we get just one side. If the denominator is odd, we get both sides. Notice that, right, 2 in the denominator was kind of like square root, and 3 in the denominator was like cube root, so it makes sense. And that's the end of 2.6. So really the biggest information here in 2.6 is regarding piecewise functions. So I know they're kind of scary. We won't be graphing a ton of them, but it is important enough that you know how to graph them, with especially that quirk that transition points need to be graphed twice. So with that said, I will see you in 2.7. Bye. Hi, everyone. Welcome back to 2.7. What we do here in 2.7 is a transformation of functions. So it's a little different from things that we've done in the past. It's kind of like puzzling to an extent, puzzling in steps. But what we did at the very end of 2.6 was looked at, a nice library of graphs of different types of functions that we can see here in algebra. But what we're going to do now is learn to transform those graphs into other very complicated looking ones. So just as some basics, right, you could always use the table method for graphing, but this becomes really tedious or difficult the harder we get. So for example, if you wanted to graph absolute value of x minus 3, this isn't so bad. But the second you want to graph something like 2 times negative x minus 6 in absolute value plus 6, that's a lot harder. So transformations is a step-by-step method that helps us graph things based on a parent function. Basically, if we start with some function that we do know, we can do some sort of transformation to get to a function that we don't know. So here are some of the things that we looked at in 2.6, right? Quadratic squaring function x squared, cubic x cubed, absolute value of x, and root functions. So knowing what the graphs of x squared, x cubed, absolute value of x, and the nth root of x look like, we could take those that we do know and kind of mesh them to look like other ones. All right, so the first type of shift we're going to talk about are rigid transformations. Rigid transformations are transformations that change the position of the graph, but not the shape. Okay, so vertical and horizontal shifts, most basic type of transformation, and you see here on this first slide, vertical shifts are going to be the most basic transformation. So vertical shifts for some function f of x, well, its transformed version, if you are vertically shifting it, would be f of x plus or minus k, right? So using g of x now instead of f of x, not to double dip. So f of x plus or minus k would be a vertically shifted function. So now the big thing here is that this plus or minus k is on the outside of the function. We're going to see some stuff where stuff happens on the inside, but for now, this plus or minus k is on the outside. If you have f of x plus k, so f of x plus k means you are taking your graph of f of x and shifting it up k units. And if we're shifting up k units, what we're doing is changing all the y values. So you would add k to all the y values to go from previous function to new function. For example, or not for example, as the opposite, if we have f of x minus k, well, f of x minus k is a shift down k units. Well, if you're shifting down, you're changing all the y values, you would subtract k units from all the y values. So this makes a lot of sense, I think, right? Plus k up, minus k down. Unfortunately, that nice intuition is not going to stick over the course of the section, but I think as a very basic type of transformation, it makes a lot of sense. Two very quick examples. X squared plus 2 would be the graph of x squared shifted up 2 units, or 2 units up, right? Either way. Absolute value of x minus 3 would be the graph of absolute value of x shifted down 3 units. Okay, so here's absolute value of x. Absolute value of x plus 2 would be take all the y values and shift them up 2 units, right? Shifting up. So 2, 2 would become 2, 4. 0, 0 would become 0, 2, right? Adding 2 to all the y values. Well, going to absolute value of x minus 3 instead, we're going to take all the y values and subtract 3 this time. So 2, 2 would become 2, negative 1. 0, 0 would become 0, negative 3. And now you see all three graphs, the original, vertically shifted up, vertically shifted down on one slide. Makes a lot of sense. Well, horizontal shifts are similar, but a little weird looking. So instead of plus or minus k on the outside, what we're going to have is minus plus on the inside. Now, that use of minus plus versus plus minus is very important, and you're about to see why. For f of x minus h on the inside, right? Again, big difference. Vertical shift plus or minus k was on the outside. This time minus plus is on the inside. If you have f of x minus h, where minus h is on the inside, this is a shift to the right h units. Okay, I am well aware that is backwards. That is uncomfortable. Vertical shifts are intuitive. They are as you'd expect. Plus k means up, minus k means down. However, horizontal shifts are counterintuitive. Minus h, you would really like to be to the left h units. That's not the case. It's backwards. So f of x shifted to the right h units, but if we're shifting to the right, that means we're taking all the x values and adding some value. So please be very careful the difference between vertical shifts and horizontal shifts. Vertical shifts, intuitive. Horizontal shifts, counterintuitive. Well, now that you know what f of x minus h is, f of x plus h would be a shift to the left h units, right? We like plus to mean right, but it doesn't here in horizontal shifts. In this case, we would subtract h from all the x values. Okay, two more quick examples. If we have x minus 4 squared, this is x minus 4 on the inside, but don't forget, minus 4 on the inside is a shift to the right 4 units. Okay, absolute value of x plus 6. We would really like plus 6 to mean to the right, but plus 6 means to the left, 6 units. Okay. So here's x squared. If we want x minus 2 squared, well, minus 2 is a shift to the right 2 units. And if we're shifting to the right 2 units, we're taking all the x values and adding 2. So adding 2 versus subtracting 2, we see the difference, I think. All right. Well, if we add 2 to 2, 4, it becomes 4, 4. If we add 2 to 0, 0, it becomes 2, 0. And now you see how that graph is shifted to the right as opposed to the left. X plus 3 squared, this is a shift to the left 3 units. So 2, 4 would become negative 1, comma 4. 0, 0 would become negative 3, comma 0. So vertical, intuitive, horizontal, counterintuitive. Unfortunately, that's not the only time this is going to happen. Okay, reflections. So reflections are another type of rigid transformation because you're not changing the shape of the graph, you're still only changing its location. For reflections over the x-axis, its transformed version is negative f of x, specifically with that negative sign on the outside. Okay, so we say f of x is reflected over the x-axis, but what we're going to do is negate each y value. Okay, so what it means to negate something is to multiply all those values by -1. I want to be careful with my wording here. I can't say make that value negative, because if I say make that value negative, you're going to think in terms of like absolute value. Absolute value says make it positive. That's not what the case is. Negation says if it's positive, if some value is positive, its negated value is negative. If an original value is negative, its negated value is now positive, right? So very careful of that. In other words, just multiply all the y values by -1. That keeps you staying careful. So that's reflections over the x-axis. Reflections over the y-axis, well, instead of negative on the outside of our function, that negative would be on the inside of the function. So we say f of x reflected over the y-axis, but instead of negating the y values, we're instead going to negate the x values. So we're going to multiply all the x values by -1. So reflections don't really take us that long. Here's f of x equals x squared. But if I want negative x squared, negative on the outside, we're going to take all the y values and multiply them by -1. Well, 0, 0 won't change, but 2, 4 will become 2, -4. Okay, square root of x. Well, what if I want square root of negative x, specifically with this negative on the inside? Well, if that negative is on the inside, we're negating the x values, right? Negative on the outside here, negate the y values. Negative on the inside, negate the x values. So what we're going to do is make all the x values negative. Well, 0, 0 stays 0, 0, but 4, 2 becomes -4, 2. And it's actually kind of interesting because normally square roots need to be all positive, but if we're taking square root of a negative x, well, square root of -4 is square root of +4, which is 2. So that's reflections. Not really scary. Now the weird one, right? The least not least intuitive, I don't want to say, but the most involved type of transformation are stretches and compressions. We refer to these as non-rigid transformations because they can change the shape of the graph, right? Vertical shifts, horizontal shifts, reflections are just taking this graph in space and just kind of moving it around, but it doesn't change the shape. It just changes where it is. But stretches or compressions will change the composition of your graph. So let's start with vertical stretches or compressions. So g of x equals c times f of x. And I think you're already seeing the pattern of this c is on the outside. So kind of like x-axis reflections, if c is greater than 0, we're going to multiply all the y values by c. If c is negative, well, think about this. If this is -2 times f of x, this is like 2 times f of x, and then reflected because that negative is on the outside. So if your c is positive, it's one step. Multiply all your y values by c. But if c is negative, you're going to multiply all the y values by absolute value of c, and technically then do a reflection where you multiply all the y values by -1. If you're strictly going for the graph, you can multiply all the y values, in this case, by -2 in one step, and that's okay. It'll have the same desired effect. However, what we're going to be interested in doing, at least in my classes watching, is understanding the order in which we do things. Well, the order in which we do things would be stretch or compression, multiplying all the y values by that constant, and then doing the reflection by -1. Now, different from class to class, that's how I prefer to teach it in my class. If the absolute value of c is bigger than 1, then what you do is stretch away from the x-axis. Your graph gets sharper, it grows quicker, so that's what it means to stretch away from the x-axis. Now, the phraseology here is going to get kind of complicated because right now we're doing vertical stretches or compressions, and then we're very shortly going to do horizontal stretches or compressions. But that's the idea here, that if your c is bigger than 1, even if it's negative, right? If this is 3, you take all the y values and multiply them by 3, it gets sharper. Even if you multiplied by -3, yeah, you would reflect, but your graph would still be sharper than the original. Likewise, if your constant is some fraction between between 0 and 1, like 1/2, well, then you're multiplying all the y values by 1/2, and if you're multiplying by 1/2, you're kind of dividing by 2. Well, in that case, you would get a lot closer to the x-axis. So if c is bigger than 1, you are stretching away from the x-axis, but vertical compression, you are going toward the x-axis. It gets closer, it doesn't grow as quick, it gets wider. That will be a compression. So here's absolute value of x. Let me move my picture. My picture still might be in the way. I really don't know how to get rid of having my picture appear twice. That's okay though. So if we wanted 2 absolute value of x, well, what we're going to do is take all the y values and multiply them by 2. So if we multiply all the y values by 2, this 1, 1 would become 1, 2. This 2, 2 would become 2, 4. And you see it got a little bit sharper. However, if I want 1/2 of x, well, this 2, 2 would become 2, 1, right? Take this y value multiplied by 1/2. 2, 2 becomes 2, 1. 4, 4 becomes 4, 2. So that would be a vertical compression because we are vertically compressing toward the x-axis. Here, we got away from the x-axis. Here, we went toward the x-axis. So away from the x-axis would be a stretch. Toward the x-axis would be a compression. Personally, if you're watching this and you're in my class, I'm not picky with how you word it. I'm more interested in the actual change itself. Okay, well, we had vertical stretches or compressions, and we have horizontal stretches or compressions, where we instead look at everything in the frame of reference from the y-axis. So instead of that c on the outside, we have a b on the inside. Okay, well, you're probably already starting to get the idea of how weird these things can be. Remember, for horizontal shifts, that -h meant add h, or to the right h, plus h on the inside meant to the left h. So for this b on the inside, if your b is positive, you are going to divide all the x values by b, right? On the inside, we're affecting x now, but instead of multiplying, we are dividing. Constantly backwards when it comes to the inside. If your b is negative, well, this is like -2x on the inside. Well, -2x on the inside would be dividing by absolute value of b and then reflecting over the y-axis by multiplying the x values by -1. Very similar to what we were just dealing with in the last part, except now x values and division instead of multiplication. If your b is bigger than 1, then you compress toward the y-axis. And this is kind of hard to picture. Its meaning isn't perfect here in algebra. We need trigonometry to really see the difference here. But for now, yes, if your b is bigger than 1, you are compressing toward the y-axis. You're getting thinner. But if your b is a fraction between 0 and 1, then you would stretch away from the x-axis and you would get a wider version of the original graph. So kind of hard to tell. But here's x squared, and if I wanted 1/2 x squared, well, this b on the inside is between 0 and 1. So our graph is going to get wider. Well, so we divide all the x values by 1/2, which is really like multiplying all the x values by 1/2 to get the same, multiplying all the x values by 2 to get the same effect. So for example, this is x equals -1, but if we're dividing by 1/2, we're multiplying by 2. To get that same y equals 1, we now need -2. And you know what? Kind of notice this too, that this is 1/2 x squared. We could have also written this as 1/4 x squared without the parentheses, and then it would have been a vertical stretch or compression. So horizontal stretches or compressions, not super meaningful here in algebraic functions because it's a little harder to tell. But again, the effects are still the same. If we had 2x squared, we are taking all the x values and dividing them by 2. So instead of x equals -1 here, it would be x equals -1/2, right? Dividing by 2 to get that same y equals 1. But also notice this could have just been like y equals 4x squared, where it's a vertical stretch or compression. So horizontal stretches or compressions, kind of weird. You're probably not going to do a lot of them here in your algebra course, but definitely those things come in handy when it comes to pre-calculus. Okay, well, the order in which we do these things is as you see it on the screen. So the original graph, you start there. Horizontal stretches or compressions, you do that first. Then reflection over the y-axis if your b is negative. Then your horizontal shift. Then vertical stretch or compression. Then x-axis reflection if applicable, and vertical shift. And one thing I want you to know is, even though this is kind of daunting looking, right? There's a lot of information on this slide. Don't worry. The order in which we do these things is the order in which you would plug something in for x. So for example, let's take this really full version right here. If you were to plug some value in for x, well, maybe if you plugged in some value for x, as written here, you would subtract h, but then again, we could distribute this b, you would multiply by b, and then subtract h. Well, multiply by b, that's the first thing we did. And then subtracting h, oh, that's the next thing we did. Okay, well, then the next thing you would do, right? Okay, so you plug in some x, you multiply by b, you subtract h, which I know this isn't how this is written here, just showing you. But then what you would do after that is apply the function, right? Square root of squared, then multiply it by c. Well, that was the next step right here, and then plus k. So order in which we do things is the order in which you apply things to x. The order in which we do these things in a nice simplified fashion is as follows. So our order, specifically for my class, right? You might in your classes be doing horizontal stretches or compressions, but like I said, they're kind of like vertical stretches or compressions in a lot of cases. Okay, so what we're going to do is start with our original graph and then do horizontal shifts. So in my case, I kind of cut out the horizontal shift. You can change, you'd be able to change horizontal stretches or compressions into vertical stretches or compressions, but in odds are you're probably not going to get that deep. Horizontal shift, first thing we do. If we have f of x minus h, add h to all the x values, right? Horizontal shifts are backwards. If you have f of x plus h, we're going to subtract h from all the x values. Vertical stretch or compression, if we have c times f of x, multiply all the y values by absolute value of c. But if your c is negative, then do an x-axis reflection and multiply all the y values by -1. Vertical shift, very last thing we do. If we have f of x plus k, we're going to add k to all the y values. F of x minus k, subtract k from all the y values, right? Again, here now that they're side by side, notice the difference between horizontal shifts and vertical shifts. Okay, so just going back, here's all those parent functions that we had, but without further ado, let's do an example. Okay, so let's graph square root of x minus 2 plus 3. We want to start with square root of x. We know what square root of x looks like. We want to work our way to this. Okay, if you don't remember the order in which we do those transformations, That's okay. The order in which we do transformations is the order in which you would do something to x when you plug it in. So for example, we plug in some x, and what's the first thing that happens to it? Well, it's not plus 3. You wouldn't take the square root of it yet. The first thing you would do is subtract 2. That's the first thing you would do to x. Now, what does x minus 2 on the inside mean? X minus 2 on the inside is a horizontal shift. And if we have minus 2, that's a horizontal shift to the right 2 units. Okay, so you plug in some x, you subtract 2, you take the square root of it, and the last thing you would do is plus 3. Plus 3 on the outside is a vertical shift up 3 units. Now, depending on your class, depending on who's teaching it, again, this one is very centric to my classes. I think I teach this kind of weird, but I hope this is still helping you. But this is one way you can write it. This is the very formal mathematical way of writing transformations. But also, if you just want to describe what's happening, you can also use it in words. So shift right 2, add 2 to the x values. Shift up 3, add 3 to all the y values. Exactly the same as what's happening in the coordinate parts, but for the description parts, you're literally describing what's happening, just not giving the function part. So in my class, if you're watching, I don't care about either. It's one way or the other. So here's square root of x. First thing we said was to shift right 2 units and then up 3. So there is our transformed version of the graph, and we didn't need to do any tables, table of values, I should say. No table of values. All we had to do is take something we already knew, shift it to the right 2, shift it up 3. And that's how transformations work. Okay, let's do another one. We have negative absolute value of x minus 2 plus 3. Parent function here, where are we going to start? Absolute value of x. Okay, now the order in which we do things is the order in which we apply things to x. So x minus 2 on the inside, right? You plug in some x and you would subtract 2 first. Well, we just saw on the previous page that subtracting 2 is a horizontal shift to the right 2 units. All right, so you have some x, you subtract 2, you take the absolute value of it, then do you do negative or plus 3? Well, you would do the multiply by a negative sign. Well, negative on the outside is a reflection over the x-axis, but if we're reflecting over the x-axis, we are multiplying all the y values by -1. We are negating all the y values. Well, last but not least, all right, you plug in an x, you subtract 2, you take the absolute value, you multiply by -1, and then you add 3 last. Okay, and then if we're adding 3 on the outside, this is a vertical shift up 3 units. And again, this is the nice mathy way of writing it, but if you wanted to give a description of what's happening, here you go. All right, here's absolute value of x. We had a horizontal shift to the right 2 units. We had an x-axis reflection, and then we went up 3. So there's our nice, finally transformed version. No table of values at all. Okay, let's do another one. 3 square root of x plus 1 minus 2. What we're going to do is start with square root of x, because that's our parent function, right? We see the square root here. First thing we would do is the plus 1, but plus 1 on the inside means shift to the left 1 unit. Then would we multiply by 3 or subtract 2? We would multiply by 3 first. And if we're multiplying by 3 on the outside, what we're doing is taking all the y values, multiplying by 3. And last but not least, -2, that's the only thing we were missing. -2 on the outside means down 2 units. There it is in words. Okay, first thing was to the left 1 unit, multiply by 3, and down 2 units. And there's our nice transformed version. So these are transformations. I think we got 1 or 2 more examples. -2, x minus 1 squared plus 3. Okay, Well, first thing you would do when you plug in an x would be the -1, start with x squared, and then we do x minus 1 squared. -1 on the inside is a horizontal shift to the right 1 unit. Then we would have -2 on the outside, but technically the order in which you would do this would be the 2 first. So we would multiply all the y values by 2, and then you would make it negative in terms of 2 separate steps. Here is the vertical stretch or compression. Here is the reflection if we're describing what's happening. So you could, if you're not looking to describe what's happening, you could do these 2 into 1 step. But again, you'll see on the next slide in terms of words how their descriptions are very different. So if you were to combine this into 1 step using like the mathy steps, it would just be x comma -2 times y. Last but not least, we got the +3 on the outside. That's a shift up 3 units. In words, here now maybe you see why we need to do it in 2 steps. Vertical stretch by a factor of 2, reflect over the x-axis. It's hard to combine those 2 into 1 step when we're using, words to describe it. All right, first thing was to the right one, then stretch by 2, reflect over the x-axis, and then up 3. And there's our nice final version of this transformed graph. So that's transformations. Transformations kind of weird, kind of quirky if you're not careful. But if you stick to doing it as a step-by-step method, it's not as bad as it seems. So with that said, thank you so much for watching, and I will see you in 2.8. Yeah, bye. Hi everyone, welcome back to 2.8. So in 2.6 and 7, we had changed gears a little bit to talk about graphs of functions, but what we're going to do is get back to doing very algebraic-based stuff, more calculation-based stuff in 2.8 and 2.9. So sections are relatively short. It's not really a ton of new information here, just some new methods, some new things we can talk about. But I wouldn't think that anything here is super scary compared to stuff we talked about, especially in 2.7. So 2.8, 2 types of things we're going to do. We're going to combine function, and we're going to compose functions. So let's start with combining functions. Well, different ways to combine functions, and they are as follows. F plus g of x. Take a wild guess what this is. And if you said it's just taking 2 separate functions and adding together, you would be correct. F minus g of x, take a wild guess, taking 2 functions and subtracting each other, okay? F times g of x, well, take 2 functions, multiply them together. F over g of x, take 2 functions and divide them. Also, you could do g minus f, where you just do g of x minus f of x, g divided by f of x, where you take g of x divided by f of x. Nothing really crazy here, but literally the 4 ways to combine functions are to add, subtract, multiply, or divide. And then we just introduce some new notation for all 4 of those. The domain of a combination function is the domain of f intersected with the domain of g. So it's not going to change a whole lot, really. We're not going to spend a whole lot of time doing domains of combination functions. It's not really that exciting. But yes, if you wanted to find the domain of a combination function, you would just take each separate domain and intersect them. The only added restriction we have for this is when we are doing division, we also want to make sure we take out all the values where g of x is 0. If g of x equals 0, then we get something undefined. Not good. So to find domain of any combination function, intersect each part. But if you're doing division, make sure the denominator does not equal 0. Also, if an x value does not appear in the domain of f or g, it cannot reappear in the domain of the combination. So here's what I mean by that. Let's say in f, you can't plug in 1. For whatever reason, you can't plug in 1. But after you do your combination, if you can all of a sudden plug in 1 and you would get something defined, well, you actually can't. Because since 1 wasn't in the original domain of f, it is not able to be in the domain of the combination, whichever combination you're doing. Of course, we're not going to do a ton of domains of combinations here, right? The more interesting part here is actually doing the combinations, at least in my opinion. So Not super crazy, but nonetheless, if you wanted to find the domain of something, just make sure that values don't reappear in your domain. So you would plug in x values the same way as you would plug in values for single functions, or you could also plug values into original functions and then do the combination. So for example, if you wanted to do f minus g of 4, this says find f minus g of x and then plug in 4. But also what you can just do is do f of 4 and then subtract g of 4. You would have the exact same effect. All right, so let's do combination functions. All right, let's say f of x, x squared minus 6x plus 8, and g of x is x minus 2. Find all 4 combinations, plus, minus, multiplication, division, and then plug in x equals 6. Well, let's just start with f plus g of x. F plus g of x says take f of x and add g of x. Well, f of x is right here. G of x is right here. So add those together. Well, negative 6x plus x is negative 5x. 8 minus 2 is 6. And we can simplify that to x minus 2 times x minus 3. And now what I want is f plus g of 6. So wherever we see x, we're going to plug in 6. 6 minus 2 is 4. 6 minus 3 is 3. 4 times 3 is 12. But also, if you're looking for a specific value of your combination, you didn't have to do it this way. So, for example, do we get 12 if we plug 6 into here, 6 into here, and then add them? Well, 6 squared is 36. 6 times 6 is 36. 36 minus 36 is 0. 0 plus 8 is 8. Okay, well, 6 over here, 6 minus 2 is 4. So 8 plus 4, by virtue of, f plus g of x, 8 plus 4 would be 12. So you could also plug values into the originals first, and then do the addition, subtraction, multiplication, division. But I think it is very good algebraic practice to actually do the combination first and then plug the value in. Okay, f plus g of 6. Oh, okay. I didn't realize I had a slide here where I actually do that. So take a second and write this slide down if you want. But yeah, you could also do it this way. All right, f minus g of x says take f of x, subtract g of x. All right, well, only difference here is that now we're going to subtract x, negative 6x minus x, negative 7x. 8 minus negative 2, 8 plus 2, which is 10, which we can factor to x minus 2, x minus 5. Now plug in 6. 6 minus 2 is 4. 6 minus 5 is 1. 4 times 1 is 4. And again, you can do this by plugging 6 into here and then plugging 6 into here, and in this case, subtracting them. Here we said we got 8. Here we got 4. 8 minus 4 is 4. Multiplication, all right. F of x times g of x would be f of x times g of x. And, well, if we want to get a nice simplified answer, I wouldn't expand this. I would just factor this one part. And, oh, actually, one thing we can do is say x minus 2 times x minus 2, x minus 2 squared. And then if I want f times g of 6, plug in 6 into here. 6 minus 4 is 2. 6 minus 2 is 4. 4 squared is 16. 2 times 16 is 32. Or you could, again, plug 6 into here, plug 6 into here, and then multiply them. 8 times 4 is indeed 32. Let's do division. Alrighty, f of x over g of x. There's f of x, there's g of x. X squared minus 6x plus 8 factors to x minus 2 times x minus 4. And we can cancel out x minus 2. Okay, well, plug in 6. 6 minus 4 is 2. And again, just doing the example of if we plugged it into here originally, plugging 6 into here gave us 8. 6 into here gave us 4. 8 divided by 4 is 2. So multiple ways to do the same thing. All right, let's do the same thing, different functions this time, and now we're going to plug in negative 2. F plus g of x, f of x plus g of x. Here's f of x, here's g of x. Let's combine like terms. And now let's plug in -2. -2 squared is 4. 3 times -2 is -6. And we get -1. So not very crazy, I don't think. Subtraction, same thing, except now we're going to subtract. Well, we just get minus 3x, but 2 minus -1 is 2 plus 1, and then plug in -2. And this is almost getting a little repetitive because we have been plugging in values for a very long time in this class. Okay, f times g of x, f of x times g of x. Take these things, multiply them together. You know what? Don't even bother. This is actually nice and factored for us already. So let's just go right for plugging in -2. -2 squared is 4. 3 times -2 is -6. 4 plus 2 is 6. -6 minus 1 is -7. -42. Okay? I don't think this is crazy to many of you watching. If you have gotten to the point of combination functions, you're probably very comfortable, adding, subtracting, multiplying, dividing, as well as plugging numbers in. One more. Let's do g over f, because why not? Let's change it up, right? Point is, it doesn't matter what I say. G over f is just g over f instead of f over g. Well, g is now at the top, f is now at the bottom, and now let's plug in 200. 3 times 200 is 600. 200 squared is 40,000. Yeah, why not? I don't know. Just plugging in numbers. Okay, let's do some combination examples, some domain examples of combinations, I should say. So if we want to find the domain of each of the 4 combinations, don't forget 3 of them are exactly the same. To find the domain of f plus g, f minus g, and f times g, what we're going to do is intersect those domains. Okay, so domain of f of x, x plus 2, the inside has to be greater than or equal to 0. So x is greater than or equal to -2, or -2 to infinity. Domain of g of x would be 5 minus x is greater than or equal to 0. X is less than or equal to 5, however you get there. So everything less than 5. Now, the domain of f plus g, f minus g, f times g is just intersect these. So the intersection of -2 to infinity, -infinity to 5 would be -2 to 5. What do those 2 domains have in common? Everything between -2 and 5. Now, for f over g, the only added restriction is that we need to make sure that the denominator does not equal 0. Well, g of x can't equal 0. Absolute value of 5 minus x can't equal 0. X just can't equal 5. Before we had -2 to 5. Well, if we now take out 5, it's just -2 to 5 with 5 no longer included. So domain of combinations, kind of weird, right? It's more important that we know how to find domains of functions in general. But yeah, now you can do it with combinations. Well, that's combinations. Let's now do composite functions. They are similar in thinking, but different way we reference them. So composite functions are literally putting one function inside another and simplifying. In combination functions, you are taking 2 functions and just adding them or subtracting them or multiplying, dividing them. But here in composite, we are plugging functions into other functions. So we have to introduce some new notation. We introduce f of g of x. F of g. And f of g of x says f of x with g of x plugged in. So this outer function with this inner function plugged in. Then we also have g of f. Same thing. We have this outer function with the inner function f of x plugged in. F of f, okay. I joke in my classes saying it's a little cannibalistic, but that's kind of what it is. You're taking f of x and you are plugging f of x into itself. And same thing for g of g. You are taking g of x and plugging it in to g of x. So f of x says take f of x, plug it into itself. G of x says plug in g of x into itself. But at least for f of g and g of f, this is taking one function and plugging it into another function. A little less weird. Okay, another way people mention these functions is fog and goff. So we use this little circle symbol to represent of. So some people like to say this is fog and Goff, which if that helps you, by all means do it. It doesn't really help you remember like f of g of x, but I also think it sounds kind of weird when you go to say like foff and gog. I don't know. Those are weird sounding uh, phrases, I guess. I don't know. So, however, it helps you remember these, but it's literally just taking this inner function, plugging into this outer function. If you want to find the domain of a composite function, you would take the domain of the inner function. So here, domain of g, here, domain of f, here, domain of f, here, domain of g, right? Whichever one is the inner function. You take the domain of the inner function and you intersect it with the domain of the final composition. All right, let's just do some composition examples. Okay, let's start with f of g of x. F of g of x says f of g of x. So this says wherever we see f, we're going to write g of x. Think back to when we originally started talking about functions. I said that f of potato says wherever we see x, plug in potato. So f of potato would be potato cubed. But now we're not plugging in just some single term. We're not plugging in like x plus h. What we're doing is plugging in g of x. So in f of x, wherever we see x, we're going to write g of x. So f of g of x would be g of x cubed. Again, wherever we see x, write g of x. But then the question is, what is g of x? Well, g of x we have a definition for. G of x is x plus 1. So we get x plus 1 cubed. Notice x plus 1 inside x cubed. But we just got to be very careful with how we talk about that. Some people some of my students in the past have been able to jump right from here to here. So if this middle step is confusing to you, that's totally fine. It's kind of hard for me to understand why that's why that is. But yeah, if you are not seeing this middle step, but you see this ending step and all the ending steps we're about to do, that's totally fine. Do as you need. Okay, so if we want to plug in x equals 2, f of g of 2 would be 2 plus 1 cubed, 3 cubed, 27. Now, there is actually another way of doing compositions like this. And what it is plug in 2 to g, and then plug that value into f. So doing that same kind of idea, 2 plus 1 is 3. 3 into x cubed is 27. So that's really what's happening. Not really anything crazy in terms of simplification going on here, but that is another way you are able to evaluate. Okay, g of f of x says take g of x, plug in f of x. Well, if this was g of potato, wherever we see x, we would write potato, but now we have g of f of x. So wherever we see x, we're going to write f of x. Okay, well, f of x plus 1, but we have a definition for f of x. F of x is x cubed. Okay, well, x cubed plus 1, now we plug in 2, and we get 8 plus 1, which is 9. Okay. F of x, this is where it starts to get a little funky. That's okay. F of x says wherever we see x, write f of x. Well, if this was f of potato, you would say potato cubed. But if f of x says f of x cubed, wherever you see x, plug in f of x. But what is f of x? F of x is x cubed. So we have x cubed cubed, which is x to the 9th. Well, if we want f of 2, just plug in 2, and 2 to the 9th is 512. 2, 4, 8, 16, 32, 64, 128, 256, 512. There we go. G of x. Okay, g of g says g with g of x plugged in. All right, well, here's g of x. G of potato would be potato plus 1. So g of x is g of x plus 1. But again, we have a definition for g of x, and that is x plus 1. So in total, x plus 2. G of 2 would be 2 plus 2, 4. Very exciting. Okay. So let's find the 4 compositions. We don't need to keep plugging in values. I think we get the idea. But let's find the 4 compositions. F of g of x says f of x with g of x plugged in. F of x is 2x plus 1, but we instead have 2g of x plus 1. And then g of x is x squared minus 3. Let's distribute 2, and negative 6 plus 1 is negative 5. G of f says g of x with f of x plugged in. Well, g of x is x squared minus 3, so g of f of x is f of x squared minus 3. But f of x is 2x plus 1. 2x plus 1 squared, that's foiling, right? Be very careful. 4x squared plus 4x plus 1, and then subtract 2 and factor out 2 just to be fancy. Looking for compositions, we can simplify, but if we're plugging in values, at some point you don't need to simplify. We're just looking for that actual value. F of x says take f of x, plug it into itself. So instead of 2x plus 1, this is 2 f of x plus 1. But f of x is 2x plus 1. Distribute 2 and add. G of g, all right. G of g says take g of x, plug it into itself. G of x is normally x squared minus 3. So the g of x plugged in, we get g of x squared minus 3. But g of x is x squared minus 3 itself. So here we're going to FOIL again and subtract 3. And that's composite functions. Okay, let's do another example. F of g of x says take f of x, plug in g of x, for x squared plus 1. Now for g of x squared plus 1, because we're plugging in g of x, but g of x is 3 minus x. All right, FOIL 3 minus x squared, multiplied by 4, and add. And we can put it back in order. G of f says take g of x, plug in f of x. So instead of 3 minus x, we get 3 minus f of x. F of x, 4x squared plus 1. 3 minus 1 is 2, and negative 4x squared. F of f says take f of x, plug it into itself, for f of x squared plus 1. F of x, though, is 4x squared plus 1. FOIL, multiply by 4, and add. And then g of g says take g of x, plug it into itself. Instead of 3 minus x, we get 3 minus g of x. G of x is 3 minus x. All right. 3 minus 3 is 0. Negative x is positive x. All righty. Let's do some domain stuff. All righty. F of x is 1 over x. G of x is 3x minus 12. If we want to find the domain of f of g of x, this is domain of the inner function g intersected with the final domain. All right. So the domain of the inner function g is all real numbers, right? This is just a polynomial. There's nothing that we can plug in that gets this in trouble. So f of g of x would be 1 over g of x, 1 over 3x minus 12. So what's the domain of 1 over 3x minus 12? 3x minus 12 can't equal 0. X can't equal 4. Everything except 4. So domain of the entire composite function would be negative infinity to infinity intersected with negative infinity to 4 with 4 to infinity. In that case, it's just negative infinity to 4 and 4 to infinity. Okay, so one very brief composite domain example. Not super exciting, but we get the idea. So that's the end of 2.8. We got one more section here in chapter 2 for inverse functions. Inverse functions are actually kind of interesting. It's the same method over and over and over again. So we're going to like that a lot. So I will see you in 2.9. Bye. Hi, everyone. Welcome back to the final section of Chapter 2. This chapter is very long. It's got a lot of really important information about functions that you need or you can't do a lot of other stuff in mathematics. So long, tedious, but it is finally coming to an end here with inverse functions. So the first thing we're going to talk about are one-to-one functions. Now, one-to-one functions are similar to functions. We're going to think about them kind of similar, except we're going to get one extra rule. So if you think back to 2.4, when we talked about functions initially, the rule we had is that every x has to go to 1y. Every x has to be used, and every x can only be used once. We had no restrictions on the y's. However, what we now introduced in 2.9 are one-to-one functions. And one-to-one functions mean that every x goes to one unique y. So in regular functions, we allow all the x's to go to the same y if we wanted to. If 1 goes to 1 and 2 goes to 1 and 3 goes to 1 and 4 goes to 1 and 5 goes to 1, that's fine. As long as every x is only used once, we're good. But now in one-to-one functions, we're restricting that every y can only be used once as well. So this is going to be the last time in this chapter that we're going to go to the whiteboard. So let's do that one more time. Okay, so for the last time here in chapter 2, don't forget that when we did functions initially, we allowed ourselves to do 1, 2, and say something like that every x was used and every x was only used once. The second we did something like this, where 1 was used twice, that wasn't a function to begin with. The second that, say, 3 doesn't go to anything, that also isn't a function to begin with. Don't forget that for just functions, every x has to be used and every x can only be used once. Now, when we're talking about one-to-one functions, the extra restriction we have is that every x can only go to one unique y. So now we're only allowing y's to be used only once. So in this example that you see on the screen right now, this isn't one-to-one because 4 is used twice. This isn't one-to-one, this is 2-to-1, right? 2 x's go to 1 y, 2-to-1. So instead, what we can do is if we have something like this would be 1-to-1. So it's as simple as that. It doesn't even need to be in that order, right? For example, 2 can go to 6 and 3 can go to 5. As long as every x is only used and every y is only used, this is a one-to-one function. So just wanted to show this off. Now we're going to get back to the presentation for the rest of the lecture. Okay, so now we're back. Just wanted to show the correspondence diagrams. That's what those little circle things are. But now let's continue. So for example, f of x equals x is 1-to-1 since every x goes to 1y. There's no way that you can make two different x's equal the same y value. However, x squared is not 1-to-1 because -2 squared is 4 and +2 squared is 4. Two x's go to one single y value. Okay, well, two ways to determine if a function is 1-to-1. We have an algebraic way and a graphical way. Algebraically, what we're going to do, we want f of a equals f of b to lead to a equals b. If this is true, then it is 1-to-1. Graphically, how we do this is the horizontal line test. So vertical line test says if our vertical pencil covers any 2 points at once, it's not a function. And likewise, horizontal line test would say if your horizontal pencil covers 2 points at once, it's not 1-to-1. Now, the big thing here to note is that a function can be a function, and it might just not be 1-to-1. That's totally okay. We'll come to what that means to not be 1-to-1 in just a moment, but just because something isn't 1-to-1 doesn't mean it's not a function. It just means it's not a 1-to-1 function. So just something to keep in mind. So let's just do some examples of determining if something is 1-to-1. So let's say we have the function 4x minus 4. What we want to do is start with f of a equals f of b and get it down to a equals b. In other words, we want to solve for a. If we get a equals b, then your function is 1-to-1. Otherwise, if you get anything else besides a equals b, it is not 1-to-1. So f of a says plug in a, f of b says plug in b. And what we can do from here to solve for a, we can add 4 to both sides. Well, that gets rid of both of the 4s. We can divide both sides by 4 and we get a equals b. So we got a equals b. In the event that f of a equals f of b leads to a equals b, your function is 1-to-1. This is the result we want. Now, you might be wondering, how on earth could we possibly get anything besides a equals b in this way? Well, let's do another one. Let's do x squared minus 2. Well, again, we start with f of a equals f of b, so we're going to plug in a and plug in b. We're going to add 2 to both sides, and then if we want to solve for a, we need to take the square root of both sides. But don't forget from the entire chapter solving equations that when we take the square root of both sides, we pick up plus and minus. Okay, so the square roots cancel out the squareds, but we now get a equals plus and minus b. This is not our desired result. Our desired result is a equals b, and we got something that isn't exactly a equals b. In that case, we would just say our function's not 1-to-1. X squared minus 2 is still a function. It's just not a 1-to-1 function, and that's okay. So the reason this is true is because f of 2 would be 2 squared minus 2, 4 minus 2, which is 2, and f of negative 2, well, negative 2 squared is also positive 4, and we get 2 that way. So even though that negative 2 and 2 both went to positive 2, the two values weren't equal to begin with, so that's not allowed for 1-to-1 functions. So that's all that is. F of x equals x cubed plus 1. Well, you might think that every exponent now is going to fail. Well, let's see. Plug in a, plug in b. Let's subtract 1 on both sides. And let's now take the cube root of both sides. But don't forget that when we take square roots and even roots, we pick up a plus and minus. But when we do cube roots, fifth roots, odd roots, we do not pick up a plus and minus. Well, in this case, the cube root and the cubed cancel each other out on both sides, and we get our desired result, a equals b. So you probably already start to see that anything that is even power might not be 1-to-1, whereas odd powers will. We'll look at those graphs in just a moment. Let's say we have f of x equals 7 over x plus 2. Well, here's what we're going to do. Same thing, f of a equals f of b. And what we're going to do is cross multiply, right? We haven't really done a whole lot of cross multiplying in this class, but let's do 7 times b plus 2 equals a plus 2 times 7. Let's divide both sides by 7, and let's subtract 2 on both sides, and we get b equals a. Okay, I know this isn't exactly a equals b, but it is basically the same thing, right? A equals plus and minus b is fundamentally different from a equals b, but b equals a and a equals b are saying the exact same thing. So this function would be 1-to-1. So just to show you graphically how these would work, again, horizontal line test says if your finger, your pencil, covers 2 points at once, it's not 1-to-1 when it's held horizontally. So here's 4x minus 4, just a line. Notice that there is no horizontal line that covers this graph at more than 1 point. X cubed plus 1, odd roots. Oh, yeah, okay, that's not so bad. But the second we got x squared minus 2, well, now we have plenty of horizontal lines that cover more than 1 point at once. So there you go. This would fail the horizontal line test. Again, x squared minus 2 is a function. It passes the vertical line test, but just because it is a function doesn't mean it's necessarily a 1-to-1 function. And there's 7 over x plus 2. Rational functions, we'll spend a little bit more time with in chapter 3, but point is not not quite anything of interest. So, all right. Well, so now we know what one-to-one functions are, but the entire purpose of the section is for inverse functions. So let's say we have the function x cubed plus 1, and when we plug in 2, we get 2 cubed plus 1, which is 9. Okay, nothing really surprising there. So 2 goes to 9, but how do we go from 9 back to 2? Well, that would be the process of taking inverses. Now, the whole reason we found one-to-one functions is because if a function is one-to-one, it has an inverse. So only one-to-one functions are what we call invertible. So if it's not one-to-one, it doesn't have an inverse. Likewise, if it has an inverse, the function is one-to-one. So the whole reason we spent all this time finding one-to-one functions is to determine whether or not a function has an inverse. Okay, we write the inverse of f of x as f inverse of x. This is not reciprocal. This is not raised to the -1. This is saying f inverse of x. And that's very different from anything else. That -1 has no algebraic property besides denoting an inverse function. Okay, so how do we find inverse functions? Well, it sounds like it could be a complicated process, but it actually isn't that bad. So to find the inverse, we have 4 steps. One of those steps is going to have multiple steps, but in general, 4 steps. Step 1, you're given f of x. Change f of x to y. You'll see why we do that in just a moment, no pun intended. You'll see why we do that in just a moment, because working with f of x can be kind of complicated for no reason. However, we know that f of x and y are the same thing, so it doesn't hurt us at all to replace f of x with y. Step 2, we're going to exchange the locations of x and y. And what I mean by that is literally wherever we see x, start writing y. Wherever we see y, start writing x. So we are literally taking all the locations and flipping them between x and y. And this is the new step to this section. So next step is to solve for y. You started with y equals something. So then after you change x and y, you get x equals something. Well, we want to get our answer back to be y equals something. Okay, so our step 1 was to get y equals. We solve for y. We have a new y equals, but those y's aren't the same. This y came from f of x. This y will be f inverse of x. Okay, so let's get right into it. F of x equals 4x minus 4. Step 1, replace f of x with y. That's the important part. That's the important start. Step 2, wherever we see y, write x. Wherever we see x, write y. So instead of y equals 4x minus 4, we are instead going to have x equals 4y minus 4. Literally switched x and y. Step 3 is going to be your longest step every time. Step 3 says solve for y. We want to get this y by itself. How we do that? We can add 4 to both sides. We can divide both sides by 4. And look at that. We got y equals. However, we have one more step. Notice that this is y equals 4x minus 4, and this is y equals x plus 4 over 4. We have y equals 2 completely separate things that are not equal to each other. In that case, this y was originally f of x. This y is f inverse of x. And that's always going to be your last step, changing y to f inverse after you have completed the process of inverting the function. Okay, let's do the same thing for x cubed plus 1. First step, change f of x to y. Step 2, wherever we see y, write x. Wherever we see x, write y. So instead of y equals x cubed plus 1, we are instead going to have x equals y cubed plus 1. From here, we're going to solve for y. We want to get this y by itself. So let's subtract 1 on both sides. Let's take the cube root of both sides. Don't forget taking cube roots, taking fifth roots, and taking odd roots. Do not add plus and minus, so nothing's wrong here. Okay, and yeah, we have y equals cube root of x minus 1. but this y is different from this y. This y was f of x. This y is f inverse of x. Okay. Well, we said this function here, x squared minus 2, wasn't 1-to-1, so it doesn't have an inverse. But let's see why. Okay. So step one, if this was to be inverted, let's say f of x equals y, step one. Step two, switch x and y. Step three, let's solve for y, so let's add 2 to both sides. And let's take the square root of both sides, but don't forget that when we take the square root of both sides, we get plus and minus. Okay, and here's where something is very wrong. This isn't a function to begin with. If it's going to be a function, if this thing right here is a function, that means when we plug in 1x, we only get 1y back, right? Vertical line test, definition of a function, we can only get 1y value for every x. So if we plugged in x equals 2, 2 plus 2 is 4, square root of 4 is 2, and we get plus and minus 2. 1x went to 2y's. That's completely illegal in terms of functions. So the inverse isn't even a function to begin with. So if the inverse is not a function, that function just doesn't have an inverse. Or, we already knew that because of the 1-to-1 thing we checked earlier. So if you try to invert a function and if it gets you to a point that it doesn't, it's not a function, that's fine. It just means it wasn't invertible to begin with, and that's very much okay. Alrighty. Well, what if we started with square root of x plus 2? Well, if we start with square root of x plus 2, we can find its inverse. Don't forget, x squared minus 2 isn't 1-to-1 to begin with, but square root of x plus 2, if you were to graph it, that is 1-to-1. So let's see what happens. Switch f of x to y, switch x and y. Let's square both sides, and let's subtract 2. Okay, well, you're probably wondering why, not literally why, x squared minus 2 is now the inverse. Well, what it comes down to is the domains of these functions. So, for example, the domain of square root of x plus 2 is negative 2 to infinity. There's only one branch to this square root of x plus 2. Well, if the domain is negative 2 to infinity, that means that this is restricted to something similar. If you start with something whose domain is all real numbers, you can have a problem at the end. But if you start with something that has a more restrictive domain, then you will get to a point that is okay. So kind of hard to explain here without showing a picture. Long story short, don't worry. In most cases, it's usually noted like, okay, when x is greater than negative 2 or something to that effect. So it works this way algebraically, but there are some quirks at hand that most likely you don't have to worry about. So instead of y equals, we have f inverse. But again, it just comes down to the definition of the function we started with versus the function we ended with, right? Starting from square root of x plus 2 is different than starting from x squared minus 2. Okay, let's do a weird one. F of x equals 7 plus the cube root of x minus 6. Step 1, switch f of x to y. Step 2, switch x and y. Step 3, solve for y. Okay, let's get the root by itself. So let's subtract 7 on both sides. We can get rid of this root by cubing both sides, right? Cubing, not a problem at all. And then we can add 6 to both sides. All right, well, this is pretty okay. Well, instead of y equals all of this y is different from this y. So we're going to change this y to f inverse. That's it. Nothing scary at all. Let's do the rational function, right? We did that earlier. We found it to be 1-to-1, so let's find its inverse. Okay, step 1, switch f of x and y. Step 2, switch x and y. Step 3 is to solve for y, and we really got to get back into our toolbox of solving for variables like we did in chapter 1. So, well, first things first, we got to get y out of the denominator here. This is kind of a problem. So why don't we multiply both sides by y plus 2? Okay, well, this y is stuck inside the parentheses, so why don't we distribute x? X times y is xy, x times 2 is 2x. Well, we want to get y by itself, so why don't we subtract 2x on both sides and then divide by x. If this was 5 times y, you would divide by 5. So just because this is an x, we can still divide by x. Okay, not so shabby. This y is different from this y. We have f inverse. Just be very careful. This isn't technically the only way you could do this. You could actually divide by x here and then subtract 2. Your answer would be equivalent, but just something to keep an eye out for. Okay, let's do it where we have x's in both cases. Oi, all right, kind of scary looking. That's fine. Step 1, switch f of x to y. Step 2, switch x and y. But this time, we're going to switch it twice, right? X appears twice, y is going to now appear twice. All right, well, kind of an issue. We got multiple y's to deal with. Let's start by multiplying both sides by y minus 5. And let's again do what we did in the last slide and distribute this x. And now notice this. We have xy here and a y right here. We want all the y's to be together. So what I'm going to do is I'm going to subtract this y on both sides, and I'm going to add 5x to both sides because we don't want the x's on the same side as y. All right, now that all of our y's are on one side together, what we can do is factor out y. Okay, not so shabby. And now, if this was y times 5, you would divide both sides by 5. However, no different. Even though this is y times x minus 1, we can just divide both sides by x minus 1. And now this new y is f inverse. Okay, not super scary, but this might be, funny. Memes, yeah, woo. All right, well, just some results of inverse functions. Not going to spend a whole lot of time doing this, but just to show you some things. If f of x is 1-to-1 and f inverse is the inverse of f of x, then here's something about domain and range. This is interesting. The domain of f of x is the range of f inverse. And that's actually kind of interesting. Likewise, the range of f of x is the domain of f inverse. Oh, that's kind of neat. Well, kind of think about this because when we were doing step 2 literally said switch x and y. Well, x is like domain, y is like range. So when you switch x and y in that step, you're changing the domain and range of f of x with itself, right? The domain became the range, x became y, and the range became the domain, y became x. So that's kind of interesting. Likewise, since we're switching x and y, this is technically a reflection over the line y equals x, which is pretty neat. So if xy is a point on f of x, then yx would be a point on f inverse. So for example, if 3, 4 is a point on the original function, then 4, 3 is a point on the inverse. Also, inverses undo their original functions. So the inverse function property says that f inverse composed with f gives you just x for every x in the domain of f of x, and f composed with f inverse also equals x for every x in the domain of f inverse. So that's why we needed to talk about compositions in the last section before we got here. Okay, just some very silly looking examples. If f of 3 equals 5, then f inverse of 5 is 3. Yeah. If f inverse of -1 is 7, then f of 7 is -1. F inverse of f of 500, assuming 500 is in the domain of f, well, that's just 500. And assuming 2000 is in the domain of f inverse, f of f inverse is 2000. Very exciting. Okay, well, if we wanted to graph the inverses, you could find the inverse and graph it, or even easier, if you already have the graph of the original function, all we need to do is reflect over the line y equals x. So how we do that is take all the x's, make them y's, make all the y's the x's, Or in other words, just flop the coordinates. 2, 4 will become 4, 2. 0, negative 4 will become negative 4, 0. And there is the graph with its inverse. X cubed plus 1, switch all the coordinates. Negative 1, 0 becomes 0, negative 1. 1, 2 becomes 2, 1. Okay. Well, we said x squared minus 2 is not invertible. We've now found it twice. It wasn't 1-to-1. Its inverse wasn't a function. Well, if we tried to do the same thing here, switching all the x's and y's with each other, we would get this. Well, this doesn't pass the vertical line test. So yeah, that's a different issue. So again, some more proof that if something isn't 1-to-1, its inverse, whatever it might be, is not a function. Okay, 7 over x plus 2. This is what the original graph looked like. When you invert it, when you switch all the x's and y's, it's actually pretty similar. Just another weird example for some obscure graph that we have here. Again, just switch all the x's and y's. -5, -5 will just stay -5, -5. But 0, -3 will become -3, 0. 3, 1 will become 1, 3. And 6, 5 will become 5, 6. Okay, and last but not least, going back to domain and range, if we think all the way back to 2.4 when we practiced finding domain, I said finding domain, very easy, but finding range is a lot more difficult. Well, here's finally the time that we can find range. Now, the only sad part is that we can only find range of 1-to-1 functions. This doesn't work for just any function. Function has to be 1-to-1 for us to find the range. Well, we saw a couple slides ago that the range of a function is the domain of the inverse. So if you want to find the range of a 1-to-1 function, you take its inverse, you take the domain of the inverse. So let's find the range of 3 over x minus 6. Well, y equals 3 over x minus 6. X equals 3 over y minus 6. Multiply both sides by y minus 6. Distribute x. Add 6x. Divide by x. So the inverse is 6x plus 3 over x. And what we're going to do is find the domain of the inverse. Again, domain of the inverse is range of the original. Okay, domain of f inverse, where is this defined? Everywhere the denominator does not equal 0, everywhere that x is not equal to 0. So the range of the original function 7 over x plus 2 is, or not 7 over x plus 2, 3 over x minus 6 is -infinity to 0 and 0 to infinity. So that's how you can find range of 1-to-1 functions. And that's finally the end of chapter 2. So a lot of information here in chapter 2, lots of small things, right? For the most part, this section wasn't too crazy. It was introducing this switch x and y step, and then it was really just a lot of algebra to finish up. So with that said, next up is one section in chapter 8 for our course that kind of goes along with solving equations and graphing a little bit, and then we'll jump to chapter 3 after that. And chapter 3 will be the last section, last chapter of the algebra course that these lectures are for. So until then, bye. Hi everyone, thank you so much for watching. I hope this lecture helped and that you learned something. Just wanted to give the brief disclaimer that this lecture for this section is based on and adapted from the section in College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Lesławska-Zerpek. So just wanted to give that disclaimer. I'm not affiliated with any of the authors. I'm not affiliated with Pearson, the publisher. This is entirely a presentation and lecture I created based on the book. So thank you so much for watching, and see you in the next section.